Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, science slows down a little, and the universe becomes a gentle place to explore before drifting off for the night. This evening, we're setting out on a journey through one of the most extraordinary collections of objects ever discovered. Not stars, not galaxies, not black holes, but planets. Countless planets. Tiny planets. Giant planets. Planets made of rock. Planets wrapped in oceans. Planets where metal rains from the sky. And planets that wander alone through the darkness with no sun at all. Before astronomers began discovering worlds beyond our own solar system, many people quietly assumed that planets would probably be fairly similar wherever you looked. Perhaps a few would resemble Earth. Others might look somewhat like Jupiter or Mars. After all, our little neighbourhood seemed like a reasonable sample of what the universe had to offer. The universe, as it often does, had other ideas. It turns out that nature is far more creative than we imagined. Some planets are so hot that their surfaces glow red in the darkness. Others are so cold that even the atmosphere freezes solid. There are worlds larger than Earth, but smaller than Neptune. Worlds with years that last only a few hours. Worlds where a sunrise might never happen because there is no nearby star to rise at all. If the cosmos were a zoo, planets would be its largest exhibit. And tonight, we're going to wander through it together. But before we begin, I'd love to know where you're listening from tonight. Are you curled up beneath a blanket while rain taps softly against a window? Perhaps you're listening from a bustling city where thousands of lights still glow beyond the glass. Maybe you're in a quiet town where the stars are visible overhead. And what time is it where you are right now? It's a fitting question for a journey like this. Because while we're all listening at different hours in different places on different schedules, we're all sharing the same small world. A rocky planet orbiting an ordinary star. One planet among trillions. If you find these sleepy explorations relaxing, interesting, or simply a pleasant way to unwind after a long day, I'd be ever so grateful if you liked the video and subscribed. It helps this little corner of calm reach other curious minds looking for a peaceful place to rest. Now, I do hope the universe doesn't become so fascinating tonight that it keeps you awake. Although if it does, at least you'll spend the extra time visiting some very unusual planets. So settle in. Let your shoulders relax. Allow the day to slowly drift into the background. And let's begin our tour of the planetary zoo. The funny thing about planets is that most of human history passed without anyone knowing just how common they really are. For thousands of years, the only planets humanity knew about were the handful visible in the night sky. Mercury, Venus, Mars, Jupiter, Saturn, the wandering stars. That's what many ancient civilizations called them. Unlike the countless fixed stars that seem permanently attached to the celestial sphere, these few bright lights slowly moved against the background. Night after night, month after month, year after year, they wandered. The word planet itself comes from a Greek term meaning wanderer, which is a rather charming name when you think about it. Ancient astronomers had no telescopes powerful enough to reveal distant exoplanets. They couldn't know that planets were everywhere. Instead, they worked with what they could see. And honestly, what they accomplished was remarkable. Babylonian sky watchers tracked planetary motions with impressive accuracy. Egyptian observers linked celestial cycles to agriculture and seasonal changes. Greek philosophers debated the nature of the wandering lights overhead. Chinese astronomers carefully recorded planetary movements across centuries. Every culture looked upward and wondered, what are those things? Why do they move? What purpose do they serve? For a very long time, nobody imagined the answer might involve trillions upon trillions of worlds. Even after the invention of the telescope, planets remained surprisingly elusive. Astronomers learned more about our own solar system. They discovered Uranus, later Neptune. Eventually Pluto, although Pluto would later receive a somewhat complicated promotion and demotion that astronomers still occasionally discuss with remarkable enthusiasm. Yet despite all those discoveries, one question remained unanswered. Do other stars have planets? It sounds like an obvious question now, Today, children grow up seeing artistic illustrations of distant planetary systems. We routinely hear news reports about newly discovered exoplanets. But only a few decades ago, nobody knew for certain. Many scientists suspected planets should exist elsewhere. After all, stars form from enormous clouds of gas and dust. Why wouldn't planets form alongside them? Yet suspicion and evidence are very different things. Astronomy is full of ideas that sound reasonable until observations prove otherwise. So astronomers needed proof, and finding that proof turned out to be astonishingly difficult. Imagine standing thousands of kilometers away from a lighthouse and trying to spot a firefly buzzing beside it. The lighthouse would completely dominate your view. The firefly would be almost impossible to detect. That is roughly the challenge astronomers face when searching for planets around other stars. Stars are bright. Planets are comparatively dim. Extremely dim. A planet may reflect light beautifully, but beside a star it practically disappears. For many years, distant planets remained hidden, not because they weren't there, because they were difficult to see. Then, in the 1990s, something changed. Astronomers finally began finding them. At first, the discoveries were rare. A single confirmed planet generated excitement throughout the scientific community. Researchers celebrated. Newspapers reported the findings. People marveled at the possibility that other worlds truly existed. Then more discoveries followed, and more, and more. The trick was realizing that planets don't have to be seen directly. Sometimes they reveal themselves indirectly. A planet's gravity tugs gently on its parent star. As the planet orbits, the star wobbles ever so slightly. Those tiny motions can be measured. In other cases, a planet passes between its star and Earth. The star's brightness dips by a tiny amount. Detect enough of those dips, and a planet announces its existence. Not loudly, more like a polite cosmic cough. Eventually the numbers began growing rapidly. Hundreds of planets became thousands. Thousands became many thousands. Today astronomers have confirmed well over 5,000 exoplanets, with countless additional candidates awaiting verification. And those are only the ones we've managed to find. Imagine standing on a beach and examining a small bucket of sand. Now imagine trying to estimate how many grains exist across every beach on Earth. That's somewhat similar to our current situation. We've discovered thousands of planets, yet the Milky Way alone likely contains hundreds of billions. Some estimates suggest there may be more planets than stars. Think about that for a moment. When you look into the night sky and see a star, there may be planets accompanying it. Several planets, maybe many planets, perhaps entire families of worlds orbiting quietly in the darkness, and our galaxy is only one galaxy among hundreds of billions. The numbers become so large that the mind starts resisting them, which is perfectly understandable. Human brains evolved to count berries and avoid predators. We weren't specifically designed for estimating planetary populations across the observable universe. Once astronomers started discovering large numbers of exoplanets, another surprise emerged. Many of them didn't resemble anything in our solar system. This was unexpected. Scientists had unconsciously treated our neighborhood as a template. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Surely other systems would look somewhat similar. A few rocky planets near the star, a few giant planets farther away. Neat, orderly, reasonable. Instead, astronomers found giant planets orbiting absurdly close to their stars. Worlds larger than Jupiter completing an orbit in only a few days. Planets with densities so low they seemed almost inflated. Massive rocky worlds unlike anything in our solar system. Entire categories that appeared common elsewhere yet completely absent here. Nature wasn't following our expectations. Nature was experimenting, and that realization transformed planetary science. The goal was no longer simply finding planets. The goal became understanding planetary diversity. Why do some worlds become rocky? Why do others become gaseous? Why are some covered in water? Why do some lose their atmospheres? Why do some migrate inward, while others remain far from their stars? What determines a planet's fate? These questions continue to drive research today. In many ways, planets resemble living things. Not literally, of course, but each one has a story. Each one experiences a unique history. Some begin large and grow larger, others suffer catastrophic collisions, some are stripped bare by stellar radiation, others remain frozen for billions of years. A planet's appearance today is often the result of countless events unfolding over immense spans of time. Take Earth. Our planet seems stable from a human perspective. Yet Earth has experienced asteroid impacts, supervolcanoes, shifting continents, changing climates, evolving oceans, and dramatic atmospheric transformations. The Earth we know today would look very different from Earth 1 billion years ago, and it may look very different again 1 billion years from now. Planets change. Given enough time, nearly everything changes. As astronomers continued surveying the galaxy, they began organising planets into broad categories. Not because every planet fits neatly into a box, nature rarely cooperates so conveniently, but categories help us understand patterns. Much like biologists classify animals, planetary scientists classify worlds, rocky worlds, gas giants, ice giants, ocean worlds, super-Earths, mini-Neptunes, lava planets, rogue planets, and several others. Each category reveals a different way nature builds a planet. Each represents a different solution to the same fundamental problem. What happens when matter gathers around a newborn star? The answer, it turns out, is almost anything you can imagine, and occasionally things you wouldn't imagine at all. There are planets where temperatures exceed thousands of degrees, planets where diamonds may form deep beneath the surface, planets where winds travel faster than sound, planets with skies that would look utterly unfamiliar to human eyes. If you could somehow visit enough worlds, eventually you would realise something rather comforting. Earth is not the standard model. There is no standard model. The universe doesn't seem interested in producing identical copies. It produces variety, endless variety. And perhaps that's one reason planetary science feels so captivating. Every discovery carries the possibility of surprise. Every newly detected world might reveal something we've never seen before. Every observation expands the map, not the map of continents or countries, the map of possibilities. At first glance, the question sounds surprisingly easy. What makes a planet a planet? After all, you've probably spent your entire life surrounded by pictures of planets. You've seen Earth from space. You've seen Jupiter's colourful storms and Saturn's rings. You've likely heard people casually refer to planets as giant balls of rock or gas-orbiting stars. Simple enough. Yet if you gather a room full of astronomers and ask for a precise definition, things become much more interesting. In fact, one of the most famous arguments in modern astronomy wasn't about black holes, aliens, or the Big Bang. It was about Pluto. Poor Pluto. Few objects in the universe have experienced such an unexpected change in public reputation. One day it was the 9th planet. The next day it seemed as though the entire astronomical community had called a meeting and decided to take away its planetary membership card. But the story of Pluto isn't really about Pluto. It's about a deeper question. What exactly separates a planet from everything else? And before we can wander through the remarkable collection of worlds scattered across the cosmos, it helps to understand where the idea of a planet begins. If we could travel backward thousands of years, long before telescopes existed, we discover that people didn't have a modern definition at all. Ancient sky watchers worked entirely with what their eyes could see. Most stars appeared fixed. Night after night, year after year, they maintained their positions relative to one another. The constellations remained recognizable, the pattern stayed intact. But a handful of bright objects behaved differently. Mercury wandered, Venus wandered, Mars wandered, Jupiter wandered, Saturn wandered. Instead of remaining fixed among the stars, they slowly shifted position over time. The Greeks called them planets, meaning wanderers. That word eventually became planet. Notice something interesting here. The original definition had nothing to do with size, nothing to do with gravity, nothing to do with orbiting stars. A planet was simply something that wandered across the sky. It was an observational category rather than a physical one. The sun was often treated similarly. The moon too. From the perspective of someone standing on Earth thousands of years ago, that made perfect sense. Nobody knew Earth itself was moving. Nobody knew planets were worlds. Nobody knew stars were distant suns. The sky was mysterious, and the wanderers were among its most curious features. As centuries passed, our understanding improved. The work of astronomers such as Nicholas Copernicus, Johannes Kepler, and Galileo Galilei gradually revealed a very different picture of reality. Earth wasn't the centre. The sun occupied the middle of the solar system. The planets orbited around it. Suddenly planets weren't wandering lights anymore. They were actual places. That shift was profound. Imagine realizing that the tiny reddish dot called Mars was not merely a point of light. It was an entire world, a place with landscapes, horizons, weather, and history. The same revelation applied to every planet. They transformed from lights into destinations. Humanity had not simply discovered new objects, we had discovered new worlds. As telescopes improved, astronomers began finding more and more members of the solar system. Some discoveries fit neatly into existing categories. Others created confusion. During the early 19th century, astronomers discovered an object between Mars and Jupiter called Ceres. Excitement spread quickly. At first, Ceres was celebrated as a new planet. Then another object appeared nearby, then another, and another. Soon astronomers realized they weren't finding isolated planets. They were finding an entire population of smaller objects. Eventually, these bodies became known as asteroids. Ceres lost its planetary status. This wasn't because Ceres changed. The object remained exactly the same. What changed was our understanding. Classification often works that way. Imagine finding a strange animal in a forest. You might initially think it's unique. Later you discover thousands of similar animals. Suddenly you create a new category. The object itself hasn't changed. Your knowledge has. Astronomy repeatedly follows this pattern. New discoveries force new definitions. Then came Pluto. When Clyde Tombaugh discovered Pluto in 1930, it seemed like a straightforward addition to the planetary family. Children learned about 9 planets. Textbooks printed diagrams. Generations grew up memorizing the sequence. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Everything appeared settled. The story should have ended there. Instead, it became more complicated. As technology improved during the late 20th century, astronomers began exploring regions beyond Neptune. What they found was surprising. Pluto wasn't alone. Far from it. The outer solar system contained countless icy objects. Some were large, some were small. Several looked remarkably similar to Pluto. Then astronomers discovered an object called Eris. Eris was comparable to Pluto. In some measurements, it even appeared slightly larger. This created a dilemma. If Pluto was a planet, shouldn't Eris be a planet too? And if Eris became a planet, what about the next similar object, and the one after that? Would the solar system eventually contain dozens of planets? Hundreds? Where exactly should the line be drawn? These questions led to one of astronomy's most famous debates. In 2006, the International Astronomical Union attempted to establish a formal definition. According to that definition, a planet must satisfy 3 requirements. First, it must orbit the Sun. Second, it must possess enough gravity to pull itself into a roughly spherical shape. Third, it must have cleared its orbital neighbourhood. That third requirement is the controversial one. What does it mean to clear an orbital neighbourhood? Imagine a child entering a playground. Eventually that child becomes so dominant that every toy nearby either belongs to them, follows them, or gets pushed elsewhere. In a gravitational sense, major planets do something similar. They dominate their orbital regions. Earth controls Earth's neighbourhood, Jupiter controls Jupiter's neighbourhood, Neptune controls Neptune's neighbourhood. Pluto, however, shares its region with many similar icy bodies. It never became gravitationally dominant. As a result, Pluto was reclassified as a dwarf planet. The reaction was immediate. Many people objected. Some felt Pluto had been unfairly demoted. Others thought the new definition made perfect sense. To this day, mentioning Pluto at an astronomy event remains a reliable way to start an interesting conversation. Yet there's something amusing about the entire debate. Pluto didn't shrink. It didn't lose mountains. It didn't lose ice. Its moons remained exactly where they were. The only thing that changed was the label humans attached to it. The universe itself seemed entirely unconcerned. Meanwhile, another challenge emerged. Astronomers started discovering planets around other stars. Thousands of them. The definition based on orbiting the Sun suddenly became awkward. After all, exoplanets orbit stars other than the Sun. Surely they count as planets. Nobody seriously wanted to argue otherwise. As a result, modern astronomy often uses a broader practical definition. A planet is generally considered a large, rounded object, formed through planetary processes that does not possess enough mass to ignite nuclear fusion like a star. That last detail is important. Stars shine because fusion occurs within their cores. Hydrogen atoms combine to form helium. Enormous energy is released. Planets never achieve the necessary mass. No matter how large a planet becomes, it remains fundamentally different from a star. This creates an interesting middle category. Objects known as brown dwarfs. Brown dwarfs occupy the blurry boundary between planets and stars. They're too massive to be ordinary planets, yet they're too small to sustain full hydrogen fusion. You might think of them as cosmic, almost stars. Nature once again refuses to provide neat boxes. Instead, it offers a spectrum, and astronomers spend a great deal of time figuring out where one category ends and another begins. What's particularly fascinating is that planets themselves are astonishingly diverse. Imagine showing an alien visitor Earth and Jupiter. Would they immediately recognize both as members of the same family? Perhaps not. Earth is a rocky world. Jupiter is a giant sphere of gas and liquid. Earth could fit inside Jupiter more than 1,000 times. Their appearances differ dramatically. Their environments differ dramatically. Their histories differ dramatically. Yet both are planets. The same applies across the galaxy. Some planets are slightly larger than Earth. Others dwarf Jupiter. Some orbit close enough to their stars that a year lasts only a few hours. Others require centuries to complete a single orbit. Some may be covered entirely by oceans. Others may contain no liquid water whatsoever. The more planets we discover, the harder it becomes to think of planets as a single type of object. Instead, they resemble an enormous family with countless variations. Dogs and whales both belong to the mammal family despite obvious differences. Likewise, rocky planets and gas giants belong to the planetary family despite their extraordinary diversity. So if planets come in so many forms, how do they begin? The answer starts inside enormous clouds of gas and dust. Throughout galaxies, vast molecular clouds drift quietly through space. These clouds contain the raw materials needed for stars and planets. Occasionally, gravity gains the upper hand. A region begins collapsing. Matter falls inward. Temperatures rise. A newborn star emerges. Around that young star, a rotating disk of leftover material remains. This disk becomes the construction site for planets. Tiny dust grains collide. They stick together. More collisions occur. Small objects become larger objects. Larger objects attract additional material. Over immense spans of time, worlds begin taking shape. The process sounds simple when summarized quickly. In reality, it is astonishingly chaotic. Countless collisions occur, some objects merge, others shatter, some migrate inward, others move outward. Entire worlds may be destroyed. New worlds may form. Planet formation resembles a construction project managed by gravity, chance, and several billion years of patience. The result can be almost anything. And that's one reason planetary diversity is so remarkable. Every planet represents the outcome of a unique history. Change one collision, move one giant planet, alter one disk slightly, you may create an entirely different world. Even within our own solar system, no two planets are truly alike. Mercury became a scorched, rocky survivor. Venus transformed into a furnace beneath a crushing atmosphere. Earth developed oceans and life. Mars evolved into a cold desert. Jupiter became a giant gravitational ruler. Saturn acquired its magnificent rings. Uranus rolled onto its side. Neptune developed fierce storms in distant darkness. Each followed a different path. Each became something unique. When astronomers search the galaxy today, they aren't merely counting planets. They're studying outcomes. They're observing what happens when nature receives raw materials and enough time. And the answer appears to be extraordinary variety. The universe does not mass-produce identical worlds. It improvises, again and again. Which brings us to an important realization. For most of history, humanity wondered whether planets existed elsewhere. Now we know they do. The question has changed. Today we ask what kinds of planets exist. How many varieties are possible? Which types are common? Which are rare? Which might support life? Which challenge our understanding entirely? Now that we've established what a planet is, or at least gotten as close as astronomers currently can, we can begin exploring the many forms planets take. And the most natural place to start is with the category of rocky worlds. Somewhere out there, at this very moment, countless rocky worlds are circling their stars. Some are blisteringly hot, some are frozen solid, some may possess mountains taller than anything on Earth. Others may be barren landscapes covered in craters that have remained unchanged for billions of years. Yet despite all their differences, rocky planets share something important. They have a surface, a real surface, not a cloud top, not an endless atmosphere gradually thickening into deeper layers. A surface you could, at least in principle, stand upon. That simple fact makes rocky worlds feel familiar. When we imagine exploring another planet, we usually picture ourselves walking across it, standing on a ridge, looking toward a distant horizon, watching the sky above. Our imaginations naturally gravitate toward rocky planets because Earth itself belongs to that family. We are creatures who evolved on solid ground. The idea of a landscape feels comfortable to us. The funny thing is that rocky planets were once considered the normal kind of planet. For much of human history, we only knew about 4 worlds that fit this category reasonably well: Mercury, Venus, Earth, Mars. They occupied the inner solar system closest to the Sun. Meanwhile, the giant planets lurked farther out. At first glance, it seemed natural to think of rocky worlds as the standard design. Then astronomers began discovering planets around other stars. What they found was surprising. Rocky planets are common, extremely common. In fact, they may be among the most common planetary outcomes in the entire galaxy. The universe appears remarkably good at making them. To understand why, it helps to travel back to the beginning of a planetary system. Imagine a young star forming inside a vast cloud of gas and dust. Around that newborn star spins a broad disk of material. Close to the star, temperatures are high, very high. Many substances simply cannot survive there. Water evaporates. Various gases remain in vapor form. Only the toughest materials endure. Metals, silicates, minerals, rocky ingredients. These resilient substances collide and stick together. Tiny particles become pebbles. Pebbles become boulders. Boulders become mountain-sized objects. Eventually gravity takes over. The growing bodies attract more material. Worlds begin to emerge. Rocky planets are essentially built from the leftovers that can withstand intense heat near a star. They are the durable survivors of planetary construction. Mercury offers an excellent place to begin. Mercury is the smallest major planet in our solar system and the closest to the Sun. If Earth were the size of a basketball, Mercury would be roughly the size of a tennis ball. For a long time, Mercury remained mysterious. The Sun's glare made observations difficult. Astronomers knew remarkably little about it. Then spacecraft finally visited. What they discovered was a world that looked surprisingly similar to Earth's moon. Mercury is covered with craters. Ancient impacts scar nearly every region. Some craters stretch hundreds of kilometers across. Gigantic cliffs slice through the landscape. The planet appears old, very old. Unlike Earth, Mercury possesses almost no atmosphere. Without wind, rain, rivers, or oceans, impact scars remain preserved for immense spans of time. A crater formed billions of years ago may still look recognizable today. Mercury also experiences astonishing temperature swings. During the day, temperatures can climb above 400 degrees Celsius. At night, they plunge below minus 170 degrees Celsius. Imagine trying to choose clothing for that forecast. A morning coat would be entirely inadequate by lunchtime. Despite its hostile conditions, Mercury remains fascinating because it reveals what a stripped-down, rocky world can look like. No oceans, almost no atmosphere, minimal geological activity, just rock, metal, gravity, and sunlight. Venus tells a completely different story. In terms of size, Venus is remarkably similar to Earth. Its diameter is only slightly smaller. Its mass is comparable. For many years, scientists wondered whether Venus might be Earth's twin. Perhaps oceans existed beneath its clouds, maybe forests, maybe life. The reality turned out to be considerably less welcoming. Venus possesses one of the most extreme environments in the solar system. Its atmosphere consists primarily of carbon dioxide. The pressure at the surface is immense. Temperatures exceed 460 degrees Celsius. That's hot enough to melt lead. And unlike Mercury, which cools dramatically at night, Venus remains relentlessly hot. Day, night, morning, evening. The temperature barely changes. The reason lies in its atmosphere. Venus demonstrates the greenhouse effect on a truly planetary scale. Sunlight enters, heat becomes trapped. The atmosphere acts like an enormous insulating blanket, an extremely effective blanket, possibly the most effective blanket in the solar system. If Mercury represents a rocky world with almost no atmosphere, Venus represents the opposite extreme, a rocky world buried beneath one. The surface itself remained hidden from human eyes until radar mapping penetrated the thick clouds. When scientists finally obtained detailed images, they found volcanoes, vast plains, mountain ranges, and evidence of dramatic geological activity. Beneath the clouds lies a genuine landscape. You just wouldn't enjoy visiting it. Earth occupies a more comfortable position, at least for us. From a cosmic perspective, Earth combines an unusual collection of features: liquid water, a breathable atmosphere, active geology, a magnetic field, moderate temperatures, life, lots of life. What's particularly interesting is that Earth isn't simply a rocky planet. It's a dynamic rocky planet. Continents move, mountains rise, oceans circulate, volcanoes erupt. Weather constantly reshapes the surface. Even the rocks beneath your feet participate in cycles spanning millions of years. Earth demonstrates that rocky planets can remain active long after formation. They are not necessarily static worlds frozen in time. Mars presents yet another variation. Today, Mars appears cold, dry, and dusty. Its atmosphere is thin. Liquid water cannot persist easily on the surface. dust storms occasionally engulf enormous portions of the planet, yet Mars preserves evidence of a different past. Ancient river valleys snake across its terrain. Dried lake basins remain visible. Minerals suggest long-term interactions with water. Billions of years ago, Mars may have possessed rivers, lakes, and perhaps even oceans. Something changed. The atmosphere gradually diminished. The climate cooled. Water disappeared from the surface. Mars became the desert world we know today. In some ways, Mars feels like a planetary cautionary tale. It reminds us that rocky planets evolve. A world that appears one way today may have looked dramatically different in the distant past. As astronomers began discovering exoplanets, they naturally searched for worlds resembling these familiar examples. Initially, that proved difficult. Large planets are easier to detect than small ones. As a result, the first exoplanet discoveries often involved giant worlds. Eventually, technology improved. Smaller planets emerged from the data, and suddenly, astronomers found rocky worlds everywhere. One famous example is Kepler 186f. Discovered in 2014, Kepler 186f attracted enormous attention because it was the first Earth-sized planet found within the habitable zone of its star. The habitable zone is often described as the region where temperatures might allow liquid water to exist. That doesn't guarantee oceans, it doesn't guarantee life, it doesn't even guarantee pleasant weather, but it does make a planet particularly interesting. Kepler 186f orbits a red dwarf star roughly 500 light-years away. Nobody knows exactly what its surface looks like. No telescope currently possesses that level of detail. Yet its discovery demonstrated something important. Earth-sized rocky planets can exist around other stars. They are not unique to our solar system. Another fascinating example is TRAPPIST-1e. TRAPPIST-1e belongs to one of the most famous planetary systems ever discovered. The star TRAPPIST-1 hosts 7 known rocky planets. 7. Imagine standing beneath a sky where neighbouring worlds might appear significantly larger than our Moon appears from Earth. Several of these planets occupy potentially habitable regions. TRAPPIST. 1e is often considered one of the most promising candidates for future atmospheric studies. Scientists are eager to learn whether it possesses an atmosphere and what that atmosphere contains. Even more remarkable is the fact that all 7 planets orbit much closer to their star than Mercury orbits our Sun. Yet because the star itself is smaller and cooler, the system remains viable. Nature continues finding new ways to arrange planets. A third famous rocky exoplanet is Proxima Centauri b. This world orbits Proxima Centauri, the closest star to our own Sun. Cosmically speaking, it's practically next door, only about 4.2 light-years away. If humanity ever sends interstellar probes toward another planetary system, Proxima Centauri b will likely be among the first targets. The planet appears roughly Earth-sized and resides within the star's habitable zone. However, red dwarf stars can be highly active. Powerful stellar flares may regularly bombard the planet. Whether Proxima Centauri b possesses a stable atmosphere remains uncertain, yet its existence remains enormously significant. The nearest star hosts a rocky planet. That fact alone tells us something about the abundance of such worlds. Then there is Kepler 452b. Often nicknamed Earth's cousin, Kepler 452b orbits within the habitable zone of a Sun-like star. It is larger than Earth and likely falls into the category known as a super-Earth, which we'll explore later. Still, it highlights an important pattern. Rocky worlds exist across a vast range of sizes. Nature doesn't stop at Earth-sized planets. Sometimes it builds larger versions, sometimes smaller ones. The diversity appears almost endless. One reason rocky planets fascinate scientists is that they provide surfaces where complex chemistry can occur. Liquid water can interact with minerals, atmospheres can evolve, climate systems can develop, volcanoes can recycle material. In short, rocky planets offer opportunities. That doesn't mean every rocky world becomes habitable. Far from it. Mercury is hostile, Venus is hostile, Mars is challenging. Many exoplanets likely endure even harsher conditions, yet rocky worlds possess possibilities that giant planets generally lack. You can stand on them, at least theoretically. You can imagine exploring them, driving across them, climbing their mountains, studying their rocks. Humans naturally relate to landscapes. Perhaps that's why rocky planets occupy such a special place in our imagination. They feel accessible, even when they're hundreds of trillions of kilometers away. What's becoming increasingly clear is that rocky planets are not rare exceptions. They appear to be one of the universe's favourite products. Given enough dust, enough time, and the right conditions, nature repeatedly assembles worlds of stone and metal. Some become infernos, some become deserts, some become frozen wastelands, some may eventually host life. And among the countless rocky planets scattered throughout the galaxy, there are undoubtedly worlds unlike anything we've imagined so far. Because as remarkable as Mercury, Venus, Earth, Mars, Kepler 186f, TRAPPIST-1e, and Proxima Centauri b may be, they represent only a tiny sample of what exists. Beyond them lie rocky worlds with entirely different histories, climates, and compositions. Far beyond the familiar landscapes of Earth, beyond deserts, mountains, canyons, and rocky plains, there may exist planets where land itself is almost non-existent. No continents, no beaches, no mountain ranges rising above the horizon, no valleys cutting across the landscape, just water. Water stretching in every direction. Water beneath the clouds, water beneath the waves, water descending so deep that no human mind has an easy way to visualize it. These are ocean planets, sometimes called water worlds, and among all the planetary types astronomers have proposed, they may be some of the most fascinating, partly because they feel familiar. After all, Earth itself is often called the blue planet. More than 70% of our surface is covered by oceans. From space, Earth appears overwhelmingly aquatic. If an alien astronomer were observing from dozens of light years away, they might reasonably classify our world as an ocean planet. Yet Earth is actually rather dry, compared to what scientists imagine when discussing true water worlds. Our oceans are impressive by human standards, but they form only a thin layer on top of a rocky planet. If Earth were the size of an apple, the combined depth of all our oceans would be thinner than the apple's skin. That realization often surprises people. We think of Earth's oceans as immense, and they are, but compared to the entire planet, they're remarkably shallow. Ocean planets take that idea and push it much further. Imagine a world where the amount of water isn't measured in oceans, it's measured in planetary layers. A world containing dozens, hundreds, or even thousands of times more water than Earth. A place where global oceans may extend hundreds of kilometers deep. A place where continents never emerge. A place where an endless sea defines the entire surface. The story of ocean planets begins during planetary formation. As we've already seen, planets form from disks of gas and dust surrounding young stars. The exact mixture of ingredients varies from place to place. Some regions contain more rock, some contain more ice, some contain more volatile materials. Far from a young star, temperatures become cold enough for water ice to survive, large quantities of it. Planetary embryos forming in these distant regions can accumulate enormous amounts of frozen water. Later, migration may move some of these worlds inward. As temperatures rise, vast quantities of ice melt. The result can be a planet wrapped in oceans on a scale that dwarfs anything in our solar system. It's important to remember that water is surprisingly common in the universe. Hydrogen is the most abundant element. Oxygen is also widespread. Combine the two, and water becomes almost inevitable. The ingredients are everywhere. Given enough time, nature manufactures astonishing amounts of it. This means ocean planets may not be rare curiosities. They could be among the most common habitable zone worlds in the galaxy. and that possibility has attracted enormous scientific interest. Before looking at distant examples, it's worth considering what life would actually be like on such a world. Imagine standing aboard a ship, not for a day, not for a week, but forever. Every direction reveals ocean. No islands appear. No coastline emerges. No mountains break the horizon. Generation after generation could pass without anyone ever seeing land. The sky above would become the primary source of geographical variety. Cloud systems, storms, sunrises, weather patterns. The ocean itself would define civilization. If intelligent life developed there, their entire history might unfold atop water. Their myths would involve water. Their transportation would involve water. Their science would begin with water. The very concept of a continent might seem as strange to them as a floating city sounds to us. Of course, such speculation remains highly theoretical. We don't know whether life exists on any ocean planet, but the possibility is intriguing, especially because water plays such a central role in life on Earth. Every known organism depends on it. Every ecosystem depends on it. Every cell depends on it. Where astronomers find water, curiosity naturally follows. One of the most famous potential ocean worlds ever discovered is Kepler 22b. Located roughly 600 light-years away, Kepler 22b became famous because it was among the first planets discovered within the habitable zone of a Sun-like star. The planet is significantly larger than Earth. Scientists aren't entirely certain of its composition. However, some models suggest it could possess enormous quantities of water, perhaps enough to create a global ocean. Nobody knows for sure. Current technology cannot directly image the surface. Yet Kepler 22b remains one of the earliest examples that encouraged astronomers to seriously consider ocean worlds as a planetary category. Another fascinating candidate is Kepler 62e. Kepler 62e orbits within the habitable zone of its star and is larger than Earth. Several studies suggest it may contain significant amounts of water. If those estimates are correct, the planet could be covered by a deep global ocean. Imagine Earth with every continent submerged. Then imagine adding vastly more water still. That's the scale researchers sometimes envision for worlds like Kepler 62e. Its sibling planet, Kepler 62f, has also attracted considerable attention. Together they demonstrate how planetary systems can produce multiple potentially water-rich worlds. Nature doesn't necessarily create one interesting planet at a time. Sometimes it builds entire collections. A third well-known candidate is TOI-1452b. Located relatively close by astronomical standards, TOI-1452b appears especially promising. Observations suggest that a substantial fraction of its mass could consist of water, not surface lakes, not oceans like Earth's, water on a planetary scale. Scientists estimate that water may account for a large percentage of the entire planet. That possibility makes TOI-1452b one of the strongest ocean world candidates discovered so far. As exciting as these examples are, they raise an important question. How deep can an ocean become? Most people instinctively imagine deeper and deeper water, a few kilometers, 10 kilometers, 20 kilometers, perhaps hundreds. But eventually something unexpected happens. Pressure. A lot of pressure. The deeper you descend into an ocean, the weight of water above increases dramatically. On Earth, the deepest part of the ocean reaches nearly 11 kilometers below sea level. Even there, pressures become immense. Ocean planets take this to extraordinary extremes. Some hypothetical oceans could extend hundreds of kilometers downward. Under those conditions, strange forms of ice begin to appear. Not ordinary ice floating in your drink. Exotic high-pressure ice. Ice that forms despite temperatures that might otherwise support liquid water. Ice that sinks instead of floats. Ice that behaves very differently from the varieties we encounter on Earth. As a result, some ocean planets may possess a layered structure. Atmosphere above, liquid ocean beneath. Then a vast shell of high-pressure ice. Only below that would rocky material finally appear. This arrangement creates one of the biggest mysteries surrounding ocean worlds. Could life emerge if liquid water never touches rock? On Earth, interactions between water and rock play an important role in planetary chemistry. Hydrothermal vents provide energy and nutrients. Minerals dissolve into oceans. Geological processes recycle essential ingredients. If thick layers of high-pressure ice separate ocean from crust, those interactions become more difficult. Scientists continue debating how that affects habitability. The answer remains uncertain. Still, uncertainty is hardly unusual in planetary science. The field is filled with questions awaiting better data. Interestingly, our own solar system contains possible miniature versions of ocean worlds. Not planets exactly, but moons. Several icy moons appear to hide enormous oceans beneath frozen surfaces. Among the most famous is Europa. Europa's icy shell conceals a global ocean beneath. That ocean may contain more water than all of Earth's oceans combined. Think about that. A moon smaller than Earth's moon, potentially containing more liquid water than our entire planet. Then there is Enceladus. Enceladus ejects plumes of water vapor into space. Spacecraft observations revealed evidence for a subsurface ocean. Researchers have detected organic compounds and signs of hydrothermal activity. Few places in the solar system generate more excitement among astrobiologists. And then there's Ganymede. Ganymede likely contains multiple ocean layers buried beneath ice. In total, it may possess more water than Earth, despite looking nothing like a blue planet from the outside. These moons remind us that water-rich worlds are not merely theoretical constructs. Nature clearly knows how to make them. The question is, how often? The answer may be very often. Planetary surveys increasingly suggest that water-rich worlds occupy a significant fraction of the galaxy's inventory. Many of the planets discovered between Earth and Neptune in size could potentially contain enormous quantities of water. Some researchers have even proposed a special category called Hycean worlds. The name combines hydrogen and ocean. These planets may possess deep oceans beneath hydrogen-rich atmospheres. Unlike Earth, their environments would be profoundly alien, yet under certain circumstances they might still support life. Hycean worlds remain hypothetical for now, but the idea illustrates how rapidly our understanding continues evolving. Every few years, astronomers uncover new possibilities, new planetary architectures, new climate models, new ways for worlds to exist. One particularly fascinating aspect of ocean planets involves weather. Earth's climate depends heavily on interactions between land and sea. Continents influence winds. Mountains redirect storms. Coastlines shape atmospheric circulation. Remove all land and the climate becomes fundamentally different. Global wind systems could operate in unfamiliar ways. Storms might grow to extraordinary sizes. Ocean currents could transport heat around the planet with remarkable efficiency. Entire climate patterns unknown on Earth might emerge. The result could be a world that appears calm from space, while hiding incredibly complex atmospheric behavior. Or perhaps the opposite, a planet wrapped in perpetual storms. Again, we simply don't know yet, and that's part of the excitement. Ocean planets sit near the boundary between observation and imagination. We know enough to believe they exist. We don't know enough to describe them with certainty. Their real possibilities awaiting future exploration. What seems increasingly clear, however, is that Earth represents only one version of a water-bearing world. For centuries, humanity unconsciously assumed that oceans and continents naturally belong together. The universe may disagree. It may produce worlds where water dominates everything, worlds where no shoreline has ever existed, worlds where endless seas stretch beneath alien skies. And yet even these immense oceans are only one solution among many, because sometimes a planet loses nearly all of its water. Sometimes entire seas disappear. Sometimes a world becomes so dry that even clouds become rare visitors. And when that happens, nature creates another familiar but very different planetary type, the desert planet. A red desert stretches beneath a pale sky. Dust drifts across the horizon. Ancient river valleys cut through the landscape, silent reminders of a wetter past. Far overhead, a small sun hangs in the sky. At first glance, this sounds like Mars, and it is. But Mars is only one example of a much larger story. Throughout the universe, there may be countless desert planets. Worlds where water is scarce, rainfall is rare or non-existent, and dry landscapes dominate nearly everything visible from the surface. Some of these planets may have begun their lives rich in oceans. Others may have formed dry from the very beginning. Some may possess thin atmospheres. Others may be wrapped in dense layers of air that contain almost no moisture at all. If ocean planets represent worlds where water won the planetary lottery, desert planets are worlds where water lost. And as strange as it sounds, these dry worlds may be among the most common planetary environments in the galaxy. The reason begins with a simple observation. Water is surprisingly fragile on astronomical timescales. Not the water molecule itself. The conditions required to keep vast quantities of liquid water on a planetary surface. Maintaining oceans for billions of years turns out to be remarkably difficult. A planet needs the right temperature, the right atmosphere, the right distance from its star. The right amount of gravity, the right geological activity, and perhaps a bit of luck. Change one factor too much and water begins to disappear. Slowly at first, then sometimes very quickly. The result can be a desert world. To understand how that happens, let's begin with the most famous example humanity has ever studied. Mars. Today Mars appears cold, dry and dusty. Its rusty colour comes from iron-rich minerals spread across the surface. Massive volcanoes rise above the surrounding plains. Canyons stretch across distances that would cover entire countries on Earth. Dust storms occasionally engulf enormous portions of the planet. Yet when spacecraft first began mapping Mars in detail, scientists discovered something unexpected. The planet looked as though rivers had once flowed across it. Not small streams, real river systems, branching channels, delta formations, ancient lake basins. Evidence appeared almost everywhere. At first, researchers were cautious. Extraordinary claims require extraordinary evidence, but decade after decade the evidence accumulated. The conclusion became increasingly difficult to avoid. Mars once possessed much more water than it does today. Billions of years ago, rivers likely flowed across its surface. Lakes existed. Perhaps even shallow oceans. A visitor arriving during that distant era might have found a world that looked dramatically different from the frozen desert we know today. So what happened? Why did Mars change? The answer involves gravity. Mars is only about half Earth's diameter and possesses much less mass. That weaker gravity made it harder to hold onto a thick atmosphere. Over time, the atmosphere gradually diminished. Without a substantial atmosphere, surface pressure fell. Without sufficient pressure, liquid water became unstable. Without liquid water, the climate changed dramatically. The planet cooled, the surface dried, the rivers vanished. What remained was a desert. A planetary-scale desert. One of the largest known in the solar system. What's particularly fascinating is that Mars still preserves evidence of its transformation. Earth is constantly reshaping itself. Rain erodes mountains, rivers carve valleys, plate tectonics recycle crust, ancient landscapes disappear. Mars, by contrast, changes much more slowly. Its dry environment acts like a museum. Features billions of years old remain visible. The planet essentially archived portions of its own history. Every dried river channel tells part of the story. Every ancient lake bed preserves another clue. Mars demonstrates something important about desert planets. Many are not born deserts, they become deserts. And that brings us to another world that may once have followed a similar path: Venus. Today, Venus is one of the most hostile places in the solar system. Surface temperatures exceed 460 degrees Celsius. Atmospheric pressure crushes with tremendous force. Clouds of sulfuric acid drift overhead. Nothing about modern Venus suggests a pleasant environment. Yet scientists increasingly suspect that early Venus may have been very different. The idea sounds surprising. After all, Venus and Earth are remarkably similar in size. They're often called sister planets. For years, researchers have wondered whether they began with similar starting conditions. If Earth developed oceans, could Venus have possessed them too? The possibility is not unreasonable. Several climate models suggest that young Venus may have supported liquid water for extended periods, perhaps hundreds of millions of years, possibly longer. If that's true, then Venus experienced one of the most dramatic climate transformations imaginable. Somewhere along the way, conditions changed, solar heating increased, water vapor entered the atmosphere, the greenhouse effect intensified. More warming produced more evaporation produced more warming. The process fed upon itself. Scientists call this a runaway greenhouse effect. Eventually the oceans disappeared. Water molecules high in the atmosphere broke apart. Hydrogen escaped into space. The planet dried out. What remained was the Venus we see today, a world so hot that many spacecraft survive only briefly after landing. If Mars represents a desert created by atmospheric loss and cooling, Venus may represent a desert created by excessive heating. Two worlds, two very different paths, the same result: a planet where surface water no longer dominates. These examples reveal an important truth. There is no single type of desert planet. The category is surprisingly diverse. Some desert worlds are cold, some are hot. Some possess thin atmospheres, some possess thick ones, some lost their water gradually, others may never have possessed much water to begin with. And once astronomers began discovering exoplanets, the possibilities expanded even further. One fascinating example is Kepler 452b. While often discussed as a potentially habitable world, some models suggest that over long periods, planets like Kepler 452b could experience increasing stellar heating as their stars age. A once temperate environment might gradually become drier. Over billions of years, even seemingly favourable worlds may transition toward desert conditions. This highlights something often overlooked. Habitability is not permanent. Planets evolve, stars evolve, climate systems evolve. What appears hospitable today may not remain hospitable forever. Another intriguing example is LHH S1140b. Scientists continue studying its atmosphere and composition. While some scenarios suggest water-rich conditions, others permit significantly drier outcomes. The challenge is that observing distant planets remains difficult. We often know their mass, we often know their size, sometimes we know atmospheric ingredients. Yet the detailed surface environment frequently remains uncertain. A distant rocky planet might possess oceans, or deserts, or something entirely unexpected. Future telescopes will help answer those questions. For now, astronomers often work with probabilities rather than certainty. One thing becoming increasingly clear is that dry worlds may be extremely common. There are several reasons for this. First, stars emit radiation. Lots of it. Over long periods, radiation can strip atmospheres and remove water. Second, planetary formation itself is chaotic. Not every world receives equal amounts of water during its creation. Some form with abundant supplies, others begin relatively dry. Third, geological activity varies enormously. A planet with vigorous geological recycling may retain water differently than a geologically inactive world. As a result, the galaxy may contain countless desert planets, occupying every imaginable stage of planetary evolution. Some may resemble Mars. Others may resemble Venus. Still others may have no solar system equivalent at all. Imagine standing on one of these distant worlds. Perhaps the sky is pale orange, perhaps it's dark blue. Maybe no clouds appear for years. Perhaps winds sculpt vast dune fields stretching thousands of kilometres. The landscape might resemble portions of Earth's Sahara Desert, or Australia's interior, or the Atacama Desert in Chile, yet on a planetary scale. Deserts large enough to cover entire hemispheres. One of the most interesting aspects of desert planets is that they are not necessarily lifeless. On Earth, deserts support a surprising variety of organisms. Life adapts. Plants conserve water. Animals avoid daytime heat. Microorganisms survive in seemingly impossible conditions. The driest deserts on Earth still contain life. This raises an intriguing possibility. Could life survive on a desert planet? The answer may be yes. Under certain circumstances, desert planets might even possess advantages. Too much water can create challenges for habitability. A completely ocean-covered world may limit certain geological interactions. A moderately dry world, by contrast, could possess stable climates and exposed land surfaces. Some researchers have proposed that partially arid planets may actually represent favourable environments for long-term habitability. This idea sometimes surprises people, because we naturally associate water with life, and rightly so. Every known organism depends upon it. Yet habitability involves balance. Too little water creates obvious problems. Too much water may create different ones. The most favourable environment might lie somewhere in between. Nature rarely prefers extremes. Another reason desert planets fascinate scientists is that they preserve planetary history. Just as Mars preserved ancient river systems, other dry worlds may preserve geological records for immense spans of time. Without abundant rainfall and erosion, ancient features survive longer. Impact craters remain visible. Volcanic structures remain intact. Tectonic patterns remain readable. In a sense, desert planets can function as planetary archives. They store information about their own past. Future explorers may one day read those records. Imagine walking across an ancient dried ocean floor on another world. Imagine standing beside a river valley that hasn't seen flowing water for 3 billion years. Imagine discovering evidence that a barren desert planet once possessed lakes, coastlines, and perhaps even life. Such discoveries would fundamentally reshape our understanding of planetary evolution, and they may eventually happen. Because desert planets appear to be everywhere, every new survey reveals additional rocky worlds orbiting distant stars. Some are undoubtedly water-rich, others are undoubtedly dry. Many likely exist somewhere between those extremes. The galaxy seems perfectly willing to produce every variation. What's especially remarkable is that Earth's future may contain lessons from both Mars and Venus. Over immense timescales, the sun will gradually become brighter, climate conditions will change, oceans will eventually diminish. The habitable Earth we know today will not last forever. That's not a cause for concern. We're discussing timescales measured in billions of years, but it does remind us that planetary evolution never truly stops. Worlds continue changing long after formation. They cool, they warm, they dry, they flood, they transform. Desert planets are simply one stage in that ongoing story. Some reached it early, others arrived later, many are probably still transitioning right now. Far beyond the comfortable warmth of Earth, beyond the deserts of Mars, beyond the giant planets that dominate the outer reaches of our solar system, there exists another category of world. A quieter category, a colder category. A place where sunlight becomes weak, temperatures plunge, and entire landscapes remain frozen for spans of time that are difficult for the human mind to comprehend. These are the ice worlds, and among all the planetary environments we know, they may be some of the most beautiful, not because they are welcoming, most certainly are not because they are easy to explore, quite the opposite. but because they reveal what happens when planetary evolution unfolds in the deep cold found near the edge of a star's influence. When we think about ice, our minds naturally jump to familiar experiences: a frozen pond, a winter morning, snow covering fields and rooftops, perhaps a distant glacier. Yet the ice found on many worlds throughout the solar system and beyond is something altogether different. It exists on scales so vast that entire planets become frozen monuments to the chemistry of the early universe. To understand these worlds, imagine gradually moving away from the Sun. Earth sits at a comfortable distance where liquid water can persist. Mars is colder. The asteroid belt lies farther still. Then come the giant planets. Beyond them, sunlight weakens dramatically. By the time sunlight reaches Neptune, it is hundreds of times fainter than what illuminates Earth. At those distances, warmth becomes a precious resource. The solar system transitions into a realm dominated by ice, not merely water ice. Many substances that are gases on Earth become frozen solids. Methane freezes, ammonia freezes, nitrogen freezes, carbon monoxide freezes. Entire landscapes can be built from materials that would seem exotic by Earth standards. An explorer visiting such a world might walk across frozen methane the way we walk across frozen lakes. Nature once again demonstrates that familiar concepts become very strange under different conditions. One of the earliest examples humanity encountered is Pluto. For generations, Pluto occupied a special place in popular astronomy. Even after its reclassification as a dwarf planet, public fascination never really disappeared. Part of that fascination comes from how unexpectedly complex Pluto turned out to be. Before spacecraft visited, many scientists imagined a relatively simple frozen world. Small, ancient, inactive. Instead, when NASA's New Horizons arrived in 2015, it revealed something remarkable. Pluto possesses mountains, plains, glaciers, atmospheric haze, evidence of ongoing geological activity. The famous heart-shaped region known as Tombor Regio immediately captured public attention. What looked like a distant point of light suddenly became a real place. A frozen place, certainly, but a place nonetheless. Perhaps the most surprising discovery involved nitrogen glaciers. On Earth, glaciers consist of water ice. On Pluto, temperatures are so low that nitrogen behaves similarly. Vast sheets of frozen nitrogen slowly flow across the landscape. The physics feels familiar, the materials do not. Pluto demonstrated an important lesson. Ice worlds are not necessarily dead worlds. They can remain dynamic. They can evolve. They can surprise us. Farther out still lies Eris. Eris helped trigger the famous planetary classification debate because its size rivals Pluto's. Yet Eris occupies an even more distant orbit. Sunlight there is extraordinarily weak. A bright afternoon on Eris would feel dim compared to what we experience on Earth. If someone could stand on its surface, the sun would appear more like an exceptionally bright star than the dominant object we know. And yet even in such distant darkness, planetary processes continue. Gravity remains active, chemistry continues. The universe never truly stops working. Another fascinating example is Makemake. Discovered in 2005, Makemake belongs to the population of icy worlds, occupying the Kuiper belt beyond Neptune. Observations suggest a surface rich in frozen methane. Again, this highlights how different these environments are from Earth. On our world, methane exists primarily as a gas. On Makemake, it becomes part of the landscape itself. Imagine mountains, plains, and frozen deposits composed partly of substances that would float invisibly through Earth's atmosphere. The farther we venture from the Sun, the stranger familiar materials become. Then there is Haumea. Haumea is one of the most unusual objects in the solar system. Instead of being roughly spherical like most large worlds, Haumea resembles a stretched oval. Its rapid rotation distorts its shape dramatically. The object spins so quickly that gravity and centrifugal force engage in an ongoing competition. The result is a world unlike anything most people imagine when hearing the word planet, yet it belongs to the same broader family of icy bodies. The same fundamental processes that created Earth also created Haumea. Different starting conditions simply produced a different outcome. These distant dwarf planets reveal an important truth. Ice worlds come in many forms. Some are small, some are large, some possess atmospheres, others do not. Some remain geologically active, others appear relatively quiet. There is no single template, only variation, and the story becomes even more interesting when we look beyond our solar system. One famous example is OGLE-2005-BLG-39OLB. This planet gained attention because it may represent one of the coldest exoplanets ever discovered. Temperatures could plunge below -200 degrees Celsius. Any water present would remain permanently frozen. The planet demonstrates that extremely cold worlds are not limited to our own planetary neighbourhood. Nature produces them elsewhere as well. In fact, they may be common. Another intriguing example is MOA-2007-BLG-192LB. This distant world likely experiences conditions far colder than those found on Earth. Scientists suspect that icy planets orbiting faint stars may be abundant throughout the galaxy. Many remain undiscovered because detecting small, distant planets remains challenging. Every improvement in observational technology reveals additional candidates. The inventory continues growing. What makes ice worlds particularly fascinating is that extreme cold doesn't necessarily eliminate all activity. On Earth, we often associate warmth with movement and cold with stillness. Planetary science tells a more complicated story. Consider Europa. Although technically a moon rather than a planet, Europa provides an excellent example of how frozen surfaces can hide active interiors. Beneath its icy shell lies a global ocean. The same may be true for several other icy moons. If similar processes occur on distant ice planets, then appearances can be deceiving. A frozen surface may conceal surprising complexity beneath. This possibility has led scientists to rethink assumptions about habitability. For many years, researchers focused primarily on Earth-like environments, moderate temperatures, liquid water on the surface, atmospheres similar to our own. Those conditions remain important. Yet discoveries involving icy worlds expanded the conversation. What if life doesn't require a surface ocean? What if subsurface oceans work as well? What if geothermal heat maintains liquid water beneath kilometers of ice? Suddenly, the number of potentially interesting worlds increases dramatically. An ice world might appear frozen and lifeless from orbit. Deep below, conditions could tell a different story. At present, we simply don't know. And uncertainty often makes science more exciting. Ice worlds also provide clues about planetary history. Many preserve ancient materials dating back to the formation of their planetary systems. Because temperatures remain low, chemical changes occur slowly. In a sense, these worlds function as cosmic archives. They retain information about conditions that existed billions of years ago. Studying them helps astronomers reconstruct the early history of planetary formation. Imagine finding a sealed time capsule buried beneath a city. Now imagine a planetary scale version of that concept. That's partly what ice worlds represent. Fragments of ancient history preserved by extreme cold. Another remarkable feature of these planets is their relationship with light. On Earth, sunlight dominates daily experience. The sun rises. The sun sets, shadows shift, colours remain vibrant. Near the edge of a planetary system, everything changes. The sky grows darker, the sun shrinks, illumination weakens. A noon sky on some ice worlds might resemble twilight by Earth standards. The environment acquires a different character entirely. A visitor standing on Pluto, for example, would experience sunlight roughly 1,600 times weaker than what reaches Earth. Yet even there, the sun remains visible, still bright enough to cast shadows, still influencing the landscape. Distance softens starlight, but it rarely removes it completely. One fascinating consequence of these low temperatures involves atmospheric behaviour. On Earth, weather occurs primarily through interactions involving water vapour. On ice worlds, entirely different substances may participate. Nitrogen may freeze and thaw seasonally. Methane may circulate through atmospheric cycles. Frosts may form from compounds unfamiliar to everyday human experience. Weather still happens, it simply uses different ingredients. Nature enjoys reusing the same physical principles while changing the materials involved. This flexibility appears repeatedly throughout planetary science. The more worlds we discover, the more we realize that Earth is one example rather than the example. Our climate works one way, other climates work differently. Our oceans consist of liquid water. Elsewhere, other liquids may dominate. Our glaciers are water ice. Elsewhere, nitrogen glaciers slowly reshape landscapes. The universe constantly reminds us that familiar concepts can appear in unfamiliar forms. Perhaps the most remarkable aspect of ice worlds is their abundance. The outer regions of planetary systems contain enormous amounts of icy material. Planet formation naturally produces frozen bodies in large numbers. Many remain small. Some grow large enough to become dwarf planets. Others may achieve full planetary status. Across the galaxy, countless stars likely host populations of icy worlds orbiting in distant darkness. Most will never be visited. Many may never even be observed directly. Yet they exist, silent participants in the ongoing story of planetary evolution. Viewed from a distance, gas giants often look calm, beautiful even. Smooth bands of colour wrap around enormous spheres. Clouds drift across their atmospheres. Sunlight reflects from layers of gas suspended high above the invisible depths below. From millions of kilometres away they can appear almost peaceful, but appearances can be deceptive. Gas giants are among the most violent, extreme and intimidating worlds ever created. These are planets where storms larger than the entire continents can rage for centuries. Worlds where lightning flashes through turbulent clouds thousands of kilometres thick. Places where pressure rises so dramatically that familiar forms of matter cease to exist. And perhaps most importantly, these are planets where a visitor could never truly stand. No matter how far you descended, no solid surface would ever appear beneath your feet. The idea feels strange because nearly every environment humans know involves a surface. We stand on ground, we climb mountains, we walk across deserts. Even ocean voyages ultimately take place above a solid planet. Gas giants challenge that intuition. They are planets without conventional surfaces, planets where the transition from atmosphere to interior happens gradually. There is no planetary equivalent of a beach waiting below the clouds, no rocky plateau, no hidden continent, just deeper and deeper layers of gas, liquid, and eventually something even stranger. To understand how these giants form, we need to return once again to the earliest days of a planetary system. Around a young star, enormous disks of gas and dust swirl through space. Close to the star, temperatures remain high. Only rocky materials survive easily. Farther out, conditions change. Water ice becomes stable. Ammonia ice becomes stable. Methane ice becomes stable. Suddenly there is far more material available for planet building. Rock and metal still exist, but now huge quantities of frozen substances join the construction project. This changes everything. Planetary cores forming in these distant regions can grow much larger than their rocky counterparts closer to the star. Once a growing world reaches sufficient mass, gravity begins pulling in vast amounts of surrounding hydrogen and helium. The process accelerates. More mass creates stronger gravity. Stronger gravity attracts more gas. The planet grows rapidly. Soon, a giant emerges, a world no longer measured merely in Earth masses, but in dozens or even hundreds of Earth masses. The result is a gas giant, and in our solar system, one gas giant stands above all others: Jupiter. If planets had a heavyweight division, Jupiter would dominate the conversation. The planet contains more than twice as much mass as every other planet in the solar system combined. Think about that for a moment. Take Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune. Add them together, then double the total. Jupiter still wins. The scale is difficult to comprehend. More than 1,300 Earths could fit inside Jupiter's volume. If Earth were the size of a grape, Jupiter would resemble a basketball. And yet even that comparison struggles to capture the reality. Jupiter isn't simply large, it is overwhelmingly large. When astronomers first observed Jupiter through telescopes, they immediately noticed something unusual. The planet wasn't featureless. Bands stretched across its atmosphere. Storm systems moved. Clouds evolved. The giant world appeared alive with motion. Centuries later, spacecraft revealed even more detail. The atmosphere turned out to be extraordinarily dynamic. Powerful jet streams race around the planet. Complex weather systems interact continuously. Gigantic storms emerge, merge, and dissipate. The most famous example is the Great Red Spot. For centuries, observers have watched this enormous storm rotate through Jupiter's atmosphere. At times, the Great Red Spot has been large enough to swallow Earth entirely. Imagine standing on Earth and looking down from space. Now imagine a single storm system larger than the entire planet beneath you. That's the scale involved, and Jupiter isn't unique. Gas giants seem remarkably talented at producing extreme weather. Part of the reason lies in their size. Larger planets contain more energy. They rotate rapidly. They possess deep atmospheres. Complex fluid dynamics emerge naturally. The result is a meteorological playground unlike anything found on rocky worlds. Of course, weather is only the beginning. The deeper mystery lies beneath the clouds. Suppose you approach Jupiter in a spacecraft. Initially, everything would seem straightforward. You'd encounter the upper atmosphere, cloud layers, winds, lightning, familiar atmospheric phenomena, albeit on a much larger scale. Continue descending, and things become more complicated. Pressure increases steadily. The atmosphere becomes denser. Temperatures rise. Hydrogen, the dominant ingredient, begins behaving differently. Eventually, the distinction between gas and liquid starts becoming blurry. There is no sharp boundary, no moment where a sign appears announcing surface ahead. Instead, the atmosphere gradually transforms into increasingly dense fluid layers. The deeper you go, the stranger conditions become. Far beneath the visible clouds lies one of the most exotic environments in the solar system: liquid metallic hydrogen. The phrase sounds like science fiction, yet researchers believe enormous quantities of metallic hydrogen exist within Jupiter's interior. Under immense pressure, hydrogen atoms are squeezed so tightly that they begin conducting electricity like a metal. This creates an enormous electrically conductive region. Combined with Jupiter's rapid rotation, the result generates an extraordinarily powerful magnetic field. In fact, Jupiter's magnetic field is so large that if human eyes could see magnetic fields, Jupiter's would appear larger than the Moon in our sky. The giant planet essentially carries its own vast magnetic environment through space. At the centre lies a core. Exactly what that core looks like remains an active area of research. Recent data suggest it may be less sharply defined than scientists once believed. Rather than a simple solid centre, Jupiter may possess a diffuse interior where materials gradually mix together. Even after decades of study, the giant world continues surprising researchers. Then there is Saturn. If Jupiter is the heavyweight champion, Saturn is the showstopper. Ask someone to draw a planet and chances are they'll sketch Saturn. The rings have become iconic. instantly recognizable, yet Saturn itself deserves just as much attention. Like Jupiter, Saturn consists primarily of hydrogen and helium. Like Jupiter, it possesses powerful storms and deep atmospheric layers. Like Jupiter, it lacks a conventional surface, yet Saturn introduces several unique features. Perhaps the most surprising is its density. Saturn is less dense than water. In theory, if you could somehow find an ocean large enough, Saturn would float. Of course, such an ocean cannot exist, but the fact remains amusing. A planet nearly 10 times wider than Earth is, on average, less dense than water. Nature clearly enjoys producing counterintuitive outcomes. Saturn's atmosphere hosts remarkable phenomena as well. One of the most famous is the Saturn hexagon. Located near the North Pole, this enormous hexagonal weather pattern has fascinated scientists for decades. A six-sided jet stream thousands of kilometers across somehow maintains its structure year after year. If someone had included such a feature in a science fiction novel before its discovery, readers might have considered it unrealistic. Yet there it is. A giant geometric weather pattern decorating one of the solar system's largest planets. The universe frequently turns out to be stranger than fiction. As astronomers expanded their search beyond our solar system, gas giants quickly became some of the easiest planets to detect. Their enormous mass influences their stars noticeably. Their large size blocks more starlight during transits. As a result, many early exoplanet discoveries involved giant worlds. And those discoveries revealed something unexpected. Not all gas giants behave like Jupiter and Saturn. Some orbit astonishingly close to their stars. One famous example is 51 Pegasi b, discovered in 1995. 51 Pegasi b transformed planetary science. The planet is roughly Jupiter-sized, yet it orbits incredibly close to its star. A year there lasts only a few Earth days. Before its discovery, many astronomers doubted such planets could exist. Theoretical models generally placed giant planets far from their stars. Nature disagreed. The discovery forced scientists to rethink planetary formation and migration. Apparently, giant planets can move, sometimes dramatically. The category became known as hot Jupiters. The name is wonderfully straightforward. They are Jupiter-like planets, and they are hot. Extremely hot. Another famous example is HD 189733b. This world has become one of the most intensively studied exoplanets ever discovered. Observations suggest temperatures exceeding 1000 degrees Celsius. Powerful winds may race through its atmosphere at several thousand kilometers per hour. Imagine a weather forecast involving supersonic winds and temperatures capable of melting many metals. Vacation brochures would likely be limited. Then there is WASP 121b. This extraordinary planet orbits so close to its star that its atmosphere is being stretched by stellar gravity. Some studies suggest metals may vaporize within its atmosphere. Clouds may contain exotic compounds unimaginable in ordinary Earth weather. The planet demonstrates how extreme gas giants can become when placed near intense stellar heat. These discoveries revealed something important. Gas giants are not a single planetary type. They occupy an enormous range of environments. Some remain cold and distant. Others become scorching hot. Some possess calm upper atmospheres. Others endure extraordinary turbulence. Some may retain stable structures for billions of years. Others may slowly lose atmospheric material to their stars. The variety seems endless. One common misconception involves the idea of falling into a gas giant. People often imagine descending through clouds until eventually reaching solid ground. The reality is far more unsettling. There may be no ground, at least not in the familiar sense. Pressure simply continues increasing. Temperatures continue rising. Materials change state. Hydrogen transforms. The environment becomes increasingly hostile. Long before reaching deeper layers, any human visitor would encounter conditions far beyond survival limits. In a sense, gas giants represent one of the few planetary categories where exploration becomes fundamentally difficult. A rover can explore Mars, a lander can visit Venus, at least briefly. A probe can touch down on icy surfaces. Gas giants offer no such opportunity. You cannot park on Jupiter, you cannot build a research station on Saturn's clouds. These worlds remain stubbornly inaccessible, and perhaps that contributes to their mystique. Even today, despite centuries of observation and decades of spacecraft exploration, much about gas giant interiors remains uncertain. The deeper layers remain hidden. Models continue improving. New observations continue refining our understanding. Yet mysteries remain. The giants still keep secrets. What's becoming increasingly clear, however, is that gas giants play a crucial role in shaping planetary systems. Jupiter's gravity influenced the formation of the solar system. It redirected asteroids, affected planetary orbits, possibly influenced the delivery of water to the inner planets. Similar processes likely occur elsewhere. A giant planet doesn't merely exist within a planetary system. It helps shape the entire system around it. In that sense, gas giants act like gravitational architects. Their presence influences countless smaller worlds. Far beyond the orbit of Saturn, beyond the dazzling rings and enormous gas giants that dominate the middle regions of our solar system, two distant worlds drift through the darkness. They appear calm from afar, blue, cold, quiet. At first glance, they almost seem like twins. Yet the more astronomers studied them, the stranger they became. These are Uranus and Neptune, the ice giants, and despite sharing a category with the larger giant planets, they are fundamentally different worlds. For many years, scientists assumed all giant planets were variations of the same basic design. Jupiter was a giant planet, Saturn was a giant planet. Uranus and Neptune were giant planets too, simple, case closed. Then spacecraft arrived. Observations improved. Computer models became more sophisticated. Gradually, researchers realized that Uranus and Neptune belong to a separate family altogether. They are not merely smaller versions of Jupiter. They represent a different planetary outcome, a different path through planetary evolution, and perhaps one of the most common planetary types in the galaxy. That last point is especially interesting. In our solar system, ice giants are relatively rare. Only 2 examples exist, yet exoplanet surveys increasingly suggest that planets similar in size and mass to Uranus and Neptune may be among the most common worlds orbiting other stars. The universe appears remarkably fond of making them, which makes understanding them even more important. The term ice giant can be slightly misleading. Many people imagine enormous frozen worlds, planet-sized snowballs drifting through space. The reality is more complicated. When planetary scientists use the word ice in this context, they aren't referring to the kind of ice you put into a drink. Instead, they mean substances such as water, ammonia, and methane that existed as frozen materials during planetary formation. These ingredients played a major role in building the planets. As a result, Uranus and Neptune contain much larger proportions of these materials than Jupiter and Saturn do. That's what separates them from the gas giants. Jupiter and Saturn are dominated overwhelmingly by hydrogen and helium. Uranus and Neptune contain more heavy materials, more water, more ammonia, more methane, different ingredients, different interiors, different planetary histories. To understand how these worlds formed, imagine once again the young solar system billions of years ago. The newborn sun sits at the centre. Around it spins an enormous disk of gas, dust, ice and rock. Closer to the sun, rocky worlds begin forming. Farther out, giant planets emerge. Beyond Saturn, temperatures become extraordinarily low. Planetary embryos growing in this region accumulate vast quantities of icy materials, yet something prevents them from becoming as massive as Jupiter. Perhaps time runs out, Perhaps the available gas becomes depleted. Perhaps planetary migration disrupts growth. Whatever the reason, Uranus and Neptune never achieved Jupiter's enormous size. Instead, they remain intermediate worlds, larger than Earth, smaller than the gas giants, a unique category between the two extremes. The first member of that category is Uranus. Few planets have a stranger personality. Most planets spin somewhat upright relative to their orbits. Earth does, Mars does, Jupiter does, Saturn does. Uranus, however, seems to have received entirely different instructions. The planet is tilted by about 98 degrees. In practical terms, Uranus rotates on its side. Imagine rolling a ball across a floor. That's roughly how Uranus travels around the Sun. Astronomers have debated the cause for years. The leading explanation involves an ancient catastrophe. Early in solar system history, a massive collision may have struck Uranus. Not a small impact, a truly colossal one. The collision could have altered the planet's orientation dramatically. If that's what happened, the consequences remain visible billions of years later. The entire planet still carries the scar of that ancient event. This unusual tilt produces bizarre seasons. Earth seasons result from a modest tilt of about 23.5 degrees. Uranus takes things much further. Each pole experiences decades of continuous sunlight, followed by decades of darkness. Imagine a summer lasting over 40 years. Then imagine a winter equally long. Life on such a world would experience time very differently. Of course, life as we know it almost certainly does not exist in Uranus's atmosphere. But the thought experiment illustrates just how alien these environments can become. When the spacecraft Voyager 2 flew past Uranus in 1986, many people were surprised by what it saw, or perhaps more accurately by what it didn't see. Compared to Jupiter and Saturn, Uranus appeared relatively plain, a smooth blue-green sphere, few obvious storms, few dramatic features. The planet almost looked sleepy. For a while, astronomers wondered whether Uranus might simply be less active than the other giant planets. Later observations complicated that picture. As telescope technology improved, researchers began detecting storms, cloud systems, and atmospheric changes. The activity was there all along. It was simply more subtle. Nature had hidden it beneath the planet's calm appearance. The blue-green colour itself comes primarily from methane. Methane molecules absorb red wavelengths of sunlight while reflecting blue and green light. The result is one of the most distinctive appearances in the solar system. A giant turquoise world drifting through the darkness. Yet even that familiar colour tells only part of the story. The atmosphere visible from space represents merely the outermost layer. Beneath it lies an environment unlike anything found on Earth. Pressure increases steadily, temperatures rise, exotic forms of matter emerge. Researchers believe the deep interior contains enormous quantities of water, ammonia and methane compressed under immense pressure. One particularly fascinating idea involves diamonds. Yes, actual diamonds. Inside Uranus and Neptune, conditions may become extreme enough to break apart methane molecules. Carbon released during this process could potentially crystallize into diamonds and sink deeper into the interior. The phrase "diamond rain" sounds like something invented for a science fiction novel. Yet planetary scientists seriously investigate the possibility. Whether large-scale diamond rain actually occurs remains uncertain. The physics suggests it might. And that's one of the joys of studying distant worlds. Sometimes reality produces concepts more imaginative than fiction. Neptune, the second ice giant, occupies an even more distant orbit. Located roughly 4.5 billion kilometers from the Sun, Neptune receives only a tiny fraction of the sunlight that reaches Earth. If Earth were illuminated by a powerful floodlight, Neptune would be lit by something closer to a distant flashlight, and yet Neptune refuses to behave like a quiet, frozen world. In fact, Neptune turned out to be one of the most dynamic planets in the solar system. When Voyager 2 arrived in 1989, astronomers expected another relatively calm giant. Instead, they found powerful storms and astonishing winds. One feature immediately attracted attention: the Great Dark Spot. Similar in some ways to Jupiter's Great Red Spot, this enormous storm system demonstrated that Neptune's atmosphere remained highly active despite its great distance from the Sun. Even more surprising were the winds. Some of the fastest winds ever measured in the solar system occur on Neptune. Speeds can exceed 2,000 kilometers per hour. That's faster than the speed of sound under many conditions on Earth. Think about that. A world receiving minimal solar energy somehow produces supersonic winds. How? The answer remains partly mysterious. Neptune appears to generate significant internal heat. In fact, the planet radiates more energy than it receives from the Sun. That extra energy helps drive atmospheric activity. The result is a surprisingly energetic world hiding within the outer darkness. One reason Neptune fascinates researchers is that it demonstrates how little we still know about giant planets. The basic picture is clear. The details remain elusive. How exactly is heat transported through the interior? What mechanisms drive the strongest storms? How do atmospheric layers interact? Scientists continue searching for answers. Unlike Jupiter and Saturn, which have received multiple dedicated missions, Uranus and Neptune have each been visited only once, a single flyby. One brief encounter. Imagine trying to understand Earth after seeing it for only a few hours. That's essentially the situation researchers face. Future missions will almost certainly transform our understanding. The ice giants are still waiting to tell much of their story. Meanwhile, discoveries beyond the solar system have elevated their importance dramatically. Astronomers repeatedly find planets occupying a similar size range. One famous example is GJ436b. Often described as a warm Neptune, GJ436b helped demonstrate that Neptune-like worlds exist elsewhere. Unlike our Neptune, however, it orbits much closer to its star. The planet experiences temperatures far higher than anything found in the outer solar system, yet its size and structure suggest similarities to the ice giant category. Another well-known example is HAT-P-11b. Observations of HAT-P-11b revealed water vapor in its atmosphere, providing valuable information about the composition of Neptune-sized worlds. Each new discovery helps fill gaps in our understanding. Gradually a broader picture emerges. Ice giants are not rare oddities. They may represent one of nature's preferred planetary designs, perhaps even more important than the familiar gas giants. That possibility would have surprised astronomers only a few decades ago. Our solar system naturally influences how we think about planets. Jupiter dominates our attention. Saturn's rings attract admiration. Yet elsewhere in the galaxy, planets closer to Uranus and Neptune may vastly outnumber both. The universe often reminds us that local experience can be misleading. What seems unusual here may be common elsewhere. What seems common here may be relatively rare. Ice giants illustrate this principle beautifully. They're familiar enough to study in detail, alien enough to challenge assumptions, common enough to matter profoundly, and mysterious enough to keep scientists busy for generations. Perhaps the most remarkable thing about Uranus and Neptune is that they occupy a middle ground. They're too large to be rocky planets, too small to be true gas giants, too warm to be frozen solid, too cold to resemble anything near Earth. They exist in a category all their own, a reminder that planetary evolution rarely follows simple rules. Nature enjoys producing worlds that blur boundaries, worlds that force us to create new classifications, worlds that reveal possibilities we never considered before. Imagine an astronomer from another civilization studying our solar system from dozens of light years away. They would detect Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. They would carefully classify the planets and begin building theories about how planetary systems form. Then they would compare our system to the thousands of others they had discovered across the galaxy, and they might come to a surprising conclusion. Our solar system is a little strange, not bizarre, not unique, but unusual enough to stand out. The reason has nothing to do with Jupiter's storms or Saturn's rings. It has nothing to do with Earth hosting life. The surprise lies in something missing. An entire category of planet appears to be absent from our neighbourhood, a category so common elsewhere that astronomers now consider it one of the most important planetary types in the galaxy. These worlds are called super-Earths. And despite their name, they are not necessarily better versions of Earth. They are simply larger, much larger in some cases, yet smaller than Neptune, occupying a middle ground that nature seems to love creating. For centuries, humanity naturally assumed the solar system represented a fairly typical planetary arrangement. Why wouldn't it? It was the only example available. Scientists could theorize about other systems, but without direct observations, there was no way to know whether our local architecture was common or rare. Then exoplanet discoveries began. Thousands of them. Suddenly astronomers had a statistical sample, not one planetary system, many planetary systems, and patterns began emerging. One pattern appeared almost immediately. Planets larger than Earth, but smaller than Neptune were everywhere. Again and again, system after system, survey after survey. The same size range kept appearing. Meanwhile, our own solar system contained nothing comparable. Earth is too small. Neptune is much larger. The gap between them exists here. Elsewhere, the gap is often filled. It was a little like discovering that nearly every city on Earth contains bicycles while your hometown somehow never acquired any. The absence becomes just as interesting as the presence. Super-Earths generally range from about 1 to 10 Earth masses. Some are only modestly larger than our planet. Others approach the boundary where Neptune-like characteristics begin emerging. That sounds straightforward enough. Yet super-Earths quickly became one of the most challenging planetary categories to understand. The problem is that size alone doesn't tell the full story. Imagine two houses that appear identical from the outside. One is built primarily from wood, the other is built from concrete. They may look similar, but their internal structures differ dramatically. Super-Earths present a comparable challenge. Two planets of similar size may possess very different compositions. Some may be rocky worlds, others may contain enormous quantities of water. Some may possess thick atmospheres, others may have relatively thin ones. The category describes size more than composition. As a result, super-Earths may represent several different planetary outcomes grouped together under a convenient label, and that's part of what makes them fascinating. Nature seems determined to keep astronomers busy. One of the most famous examples is Kepler 452b. When Kepler 452b was announced, headlines appeared across the world. Many reports referred to it as Earth's cousin. The comparison wasn't entirely accurate, but it captured public imagination. The planet orbits within the habitable zone of a star somewhat similar to our Sun. Its diameter is significantly larger than Earth's. Scientists estimate it may be roughly 60% wider. That difference might not sound dramatic at first. After all, 60% isn't an enormous number. But planetary volume grows rapidly with size. A slightly larger planet can contain vastly more material. Kepler 452b may possess several times Earth's mass. Its gravity could be substantially stronger. A person visiting such a world might immediately notice the difference. Walking would feel heavier. Jumping would become more difficult. Every movement would require additional effort. And yet the horizon might still feel strangely familiar. That's one reason super-Earths capture attention. They're large enough to be different, small enough to remain relatable. Another remarkable example is 55 Cancri e. If Kepler 452b sounds potentially comfortable, 55 Cancri e definitely does not. This world orbits extraordinarily close to its star. A year there lasts less than a day and a half. temperatures reach astonishing levels. The surface may contain vast regions of molten rock. Some early studies even sparked speculation about carbon-rich compositions and possible diamond-rich interiors. Later observations complicated that picture, but the planet remains one of the most extreme super-Earths ever discovered. Imagine standing on a world where the landscape itself glows with heat, where rock behaves more like a slow-moving fluid than a stable surface, where the star dominates the sky with overwhelming brightness. This is not Earth enlarged, it is something entirely different. Then there is LHS 114OB. This planet has attracted considerable interest because it may be one of the most promising rocky worlds discovered so far. Located roughly 48 light-years away, LHS 114OB receives enough stellar energy to maintain potentially moderate temperatures. Researchers continue studying its atmosphere and composition. Future telescopes may reveal much more. For now, it remains one of the leading examples of a super-Earth that could possess conditions somewhat favourable for liquid water. The key word, as always, is could. Planetary science teaches humility. Until observations improve, certainty remains rare. Still, the possibilities are exciting. Another famous member of the family is Gliese 667cc. For years, Gliese 667cc appeared on lists of particularly intriguing exoplanets. The planet orbits within a region where temperatures may permit liquid water. Its mass exceeds Earth's substantially. Yet despite the additional size, it remains much closer to the rocky end of the planetary spectrum than to the giant planets. Discoveries like this help transform scientific thinking. Before exoplanet surveys, researchers had only a vague idea of what planetary diversity might look like. Now entirely new categories were appearing. Not theoretical categories, real ones, observed ones, measured ones. One reason super-Earths are so common may involve the mechanics of planetary formation. Building an Earth-sized planet requires a significant amount of material. Building a Neptune-sized planet requires even more. Somewhere between those extremes lies a sweet spot, a region where growing worlds can accumulate substantial mass before running out of building materials. Many planetary systems may naturally produce planets in this range. Not because nature specifically prefers them, because the formation process frequently ends there. Think of it like baking. Suppose a particular recipe naturally produces loaves of a certain size most of the time. You can create larger or smaller versions under special circumstances, but the standard outcome appears again and again. Planet formation may behave similarly. Super-Earths might simply represent one of nature's most efficient products. Yet despite their abundance, we know surprisingly little about them. The reason is straightforward. Distance. Even the closest examples remain unimaginably far away. Astronomers can estimate mass, measure size, analyze portions of atmospheres, detect temperatures, infer possible compositions. But nobody has ever seen a super-Earth surface directly. Not in detail. Not the way we have seen Mars. Not the way we have mapped the Moon. Every image you've ever seen of a super-Earth is an artist's interpretation, an educated guess. Sometimes a very sophisticated guess. Still a guess. That fact creates an unusual situation. Super-Earths may be among the most common planets in the galaxy, yet they remain largely mysterious. We know they exist. We know roughly how large they are. Beyond that, many questions remain unanswered. What do their landscapes look like? Do they possess mountains, oceans, deserts, active volcanoes, global cloud systems? How strong is their gravity? How thick are their atmospheres? What colours dominate their skies? Nobody knows for certain, and that uncertainty fuels imagination. Consider gravity for a moment. A larger rocky planet would likely possess stronger surface gravity than Earth. Not dramatically stronger in every case, but enough to matter. Mountains might behave differently. Atmospheres might remain thicker. Escaping into space becomes more difficult for gases. Over billions of years, those small differences can reshape planetary evolution. The atmosphere a world retains affects climate. Climate affects geology. Geology affects chemistry. Everything connects. Change one variable and the entire story shifts. Some super-Earths may possess enormous mountain ranges. Others may remain relatively smooth. Some may support deep oceans. Others may become arid deserts. The category itself tells us very little about the details, only the scale. That's why astronomers often compare super-Earths to unopened books. We can read the title. We know approximately how long the story is. The contents remain largely unknown. Future observatories will gradually change that. Already, powerful instruments are beginning to analyse exoplanet atmospheres in unprecedented detail. The James Webb Space Telescope has opened new possibilities. Researchers can now examine atmospheric chemistry with a precision that would have seemed extraordinary only a generation ago. As techniques improve, some of the mystery surrounding super-Earths will begin disappearing. Not all of it, but some. One particularly intriguing possibility involves habitability. Could super-Earth support life? The answer appears to be yes, at least in principle. Nothing about being larger than Earth automatically prevents habitability. In fact, some researchers have argued that certain super-Earths may offer advantages. Stronger gravity could help retain atmospheres. Greater internal heat could sustain geological activity for longer periods. Larger worlds might remain geologically alive long after smaller planets become inactive. Of course, larger size can also create challenges. Too much atmosphere, too much pressure, too much greenhouse warming. Planetary science rarely provides simple answers. Every advantage carries potential complications. Nature excels at trade-offs. Still, the possibility remains. Somewhere among the countless super-Earths orbiting distant stars, there may be worlds with oceans, weather systems, and stable climates, perhaps even biospheres. At present, we simply lack the data to know. What's remarkable is how quickly super-Earths transformed from hypothetical objects into a major branch of planetary science. A few decades ago, nobody knew they existed. Today they represent one of the most important categories in exoplanet research. Thousands of observations continue refining our understanding. New discoveries appear regularly, and every discovery reinforces the same lesson. The solar system is not the universal template we once imagined. It is one arrangement among many, one solution among countless possibilities. Super-Earths demonstrate that clearly. Nature repeatedly builds worlds larger than Earth, yet smaller than Neptune, worlds absent from our own neighbourhood. Worlds that may outnumber all familiar terrestrial planets, worlds that remain frustratingly distant and endlessly fascinating. Long before astronomers discovered thousands of planets orbiting distant stars, the solar system quietly convinced us that we understood how planetary systems worked. There were small rocky planets near the Sun. There were giant planets farther out. The arrangement seemed logical, neat, orderly, almost textbook perfect. Mercury, Venus, Earth, Mars, then Jupiter, Saturn, Uranus, Neptune. The pattern appeared so natural that many scientists unconsciously assumed other planetary systems would follow roughly the same design. Perhaps a few variations would exist here and there. Maybe a giant planet would sit slightly closer to its star. Maybe a rocky world would be a little larger or smaller than Earth. But surely the overall structure would look familiar. Then the exoplanet discoveries began. And once again, the universe responded with a polite but firm reminder that it had never agreed to follow our expectations. Among the earlier surprises was the realization that one of the most common planetary types in the galaxy doesn't exist anywhere in our own solar system. Not a single example. Not one. These worlds are called mini-Neptunes, and they may represent one of the greatest missing pieces in our local planetary collection. The name itself provides a useful clue. Mini-Neptunes resemble smaller versions of Neptune. That sounds simple enough. Yet the category occupies a fascinating middle ground. Mini-Neptunes are generally larger than Earth, often significantly larger, but smaller than Neptune itself. They possess substantial atmospheres composed primarily of hydrogen and helium. Unlike rocky super-Earths, which may have relatively thin atmospheres and solid surfaces near the top of their structure, mini-Neptunes are wrapped in thick gaseous envelopes. In many cases, those atmospheres may account for a surprisingly large fraction of the planet's overall size, and that's where things become interesting. Imagine two planets. One is a super-Earth, the other is a mini-Neptune. Their diameters might look similar. At first glance, they could appear almost identical, yet their environments may be completely different. The super-Earth might possess mountains, oceans, deserts, or continents. The mini-Neptune might have no accessible surface at all. One world could feel somewhat familiar, the other might resemble a scaled-down giant planet. Distinguishing between these possibilities remains one of the most important challenges in modern planetary science. Part of the difficulty comes from the fact that planets don't carry labels. Nature never announces this one is a super-Earth, or this one is a mini-Neptune. Astronomers must infer planetary characteristics using measurements of size, mass, density, and atmospheric composition. Sometimes the answer is clear, often it is not. The boundary between categories can be surprisingly fuzzy, and that fuzziness reveals something important. Planetary evolution is not a collection of neat boxes, it is a continuum, a spectrum. Nature enjoys producing worlds that sit somewhere between familiar categories. Mini-Neptunes are excellent examples of this tendency. One of the most famous discoveries in this category is GJ1214b. Few planets have played a larger role in shaping scientific understanding of mini-Neptunes. When astronomers discovered GJ1214b in 2009, excitement spread quickly. The planet was roughly 2.7 times the diameter of Earth. Its density suggested something unusual. It appeared too light to be a purely rocky world. Yet it was far smaller than Neptune. The discovery highlighted a new category, sitting between familiar planetary types. Since then, GJ1214b has become one of the most extensively studied exoplanets in astronomy. Researchers have spent years trying to understand its atmosphere. Clouds appear to obscure much of the view. Observations suggest a thick gaseous envelope surrounding the planet. Exactly what lies beneath remains uncertain, and that uncertainty makes the planet even more valuable scientifically. Every new observation helps refine our understanding. Another fascinating example is K2-18b. This world has attracted enormous attention in recent years. The reason is simple. K2-18b orbits within a region where temperatures might allow liquid water under certain conditions. That immediately makes scientists curious. Not because anyone believes the planet resembles Earth, it almost certainly does not, but because understanding atmospheric chemistry on such worlds could reveal entirely new planetary environments. Recent observations from the James Webb Space Telescope have provided increasingly detailed information about K2-18b's atmosphere. Researchers continue debating exactly what those observations mean, and that's often how science progresses, not through immediate certainty, through careful investigation, question by question, observation by observation. A third important example is TOI-270d. This planet belongs to a fascinating planetary system containing multiple worlds of different sizes. Systems like TOI-270 help astronomers study planetary formation directly. Why did one planet become one thing while its neighbour became something else? Why did atmospheric evolution proceed differently? What role did distance from the star play? Planetary families often reveal more than isolated planets because comparisons become possible. Nature provides a laboratory. Astronomers try to interpret the results. What's especially remarkable is how common mini-Neptunes appear to be. As exoplanet surveys expanded, scientists noticed a recurring pattern. Planets between Earth and Neptune in size kept appearing, again and again. Thousands of them. In fact, statistical studies now suggest that mini-Neptunes may be among the most abundant planetary types in the Milky Way. Think about that for a moment. One of the most common kinds of planet in the galaxy does not exist in our solar system. Imagine discovering that one of the most common animals on Earth lived everywhere except your own continent. You would immediately want to know why. Planetary scientists ask exactly that question. Why doesn't the solar system contain mini-Neptunes? The answer remains uncertain. Several possibilities exist. Perhaps Jupiter's formation altered the early architecture of the solar system. Perhaps planetary migration unfolded differently here. Perhaps certain conditions prevented intermediate worlds from retaining thick atmospheres. Researchers continue investigating. The absence itself has become an important clue. Sometimes what isn't present tells you as much as what is. One reason mini-Neptunes fascinate scientists is that their atmospheres can be enormous relative to the planet beneath. Imagine Earth wrapped in a hydrogen-helium atmosphere thousands of kilometers thick. The planet's radius would increase dramatically, yet much of that additional size would consist of gas. This creates an interesting consequence. Size alone can be misleading. A mini-Neptune may appear much larger than Earth, while containing only a modestly larger rocky core. The atmosphere does much of the work. It's a bit like comparing a balloon and a stone. One appears larger because of its outer layers. Understanding these atmospheric envelopes has become a major focus of exoplanet research. Hydrogen and helium are incredibly light. Young planets often acquire them easily. The question is whether they keep them. Smaller worlds struggle to retain gases over long timescales. Stellar radiation gradually strips atmospheres away. Larger worlds hold on more effectively. Mini-Neptunes seem to occupy a particularly interesting balance point. Massive enough to retain significant atmospheres, small enough to remain distinct from giant planets. This balance may explain their abundance. Nature frequently builds planets in this range. Some retain thick atmospheres, others lose them. And that process may create another fascinating phenomenon. Scientists increasingly suspect that many super-Earths and mini-Neptunes are closely related. They may even represent different evolutionary outcomes for similar starting worlds. Imagine two young planets forming with comparable masses. One retains most of its atmosphere. It becomes a mini-Neptune. The other loses much of its gaseous envelope. The rocky core becomes exposed. It becomes a super-Earth. The distinction may sometimes reflect history more than origin. This idea gained support when astronomers identified something called the radius valley. When plotting exoplanet sizes, researchers noticed a curious gap. Planets tend to cluster around certain sizes. A relative shortage exists between those groups. Many scientists interpret this pattern as evidence of atmospheric loss. Some worlds remained mini-Neptunes, others transformed into super-Earths. Few remained in between. It's one of the clearest examples of planetary evolution visible in current exoplanet data. The concept reveals something profound. Planets are not static objects. They change. Atmospheres evolve. Stars influence them. Radiation reshapes them. What a planet becomes depends partly on where it begins and partly on what happens afterward. Mini-Neptunes illustrate that beautifully. Another intriguing aspect involves weather. On Earth, weather occurs within a relatively thin atmospheric layer. Mini-Neptunes may possess atmospheres extending thousands of kilometers deep. Cloud systems could form from materials unfamiliar to terrestrial meteorology. Temperatures might vary dramatically with depth. Powerful winds could circulate through enormous atmospheric volumes. In some cases, atmospheric pressures become so extreme that entirely new chemical behaviors emerge. Trying to imagine such environments stretches the limits of intuition. Human experience offers few useful comparisons. And yet those worlds may be incredibly common. Entire classes of planetary weather may exist throughout the galaxy, without any equivalent in our own solar system. That realization remains one of the most exciting consequences of exoplanet discovery. Every new category expands our understanding of what planets can be. A few decades ago, mini-Neptunes were hypothetical. Today they are central to planetary science. Future observatories will reveal even more. Researchers hope to measure atmospheric compositions with increasing precision. Cloud structures, temperature profiles, chemical signatures, perhaps even hints about planetary origins. The next generation of telescopes may transform mini-Neptunes from mysterious statistical objects into richly characterized worlds, and there is much left to learn. Do some possess deep global oceans beneath their atmospheres? Do others transition directly into exotic high-pressure interiors? How diverse are their climates? What determines whether a planet becomes a mini-Neptune rather than a super-Earth? The questions continue multiplying, which is usually a sign that a field is healthy. Good science often generates more questions than answers. What's becoming increasingly clear, however, is that mini-Neptunes represent one of nature's favourite planetary designs. Not giant enough to become Jupiters, not small enough to resemble Earth. Instead, they occupy a middle ground all their own, a category absent from our local neighbourhood yet abundant throughout the galaxy, a reminder that our solar system is only one example among countless possibilities. There are places in the universe where the ground never truly becomes solid, not because those worlds lack rock, not because they are made of gas, but because they are simply too hot. The heat is relentless, day after day, year after year, million after million of years. The surface remains trapped in temperatures so extreme that mountains soften, minerals melt, and entire landscapes behave more like oceans than continents. On these worlds, rock flows like water. Welcome to the realm of lava planets. Among all the planetary types discovered so far, lava worlds rank among the most dramatic. They are places where the familiar rules of geology begin to break down. The distinction between land and liquid becomes blurry. The horizon may glow red beneath a dark sky. Rivers of molten stone can stretch across enormous distances. Some of these planets are so hot that portions of their surfaces literally vaporize. In a sense, they are worlds caught in a permanent state of geological catastrophe, and unlike volcanic eruptions on Earth, where molten rock appears briefly before cooling, lava planets can remain trapped in this condition indefinitely. The reason usually comes down to one simple factor: distance, or more specifically, the lack of it. Most lava planets orbit extraordinarily close to their stars, much closer than Mercury orbits the Sun, in some cases astonishingly closer. To appreciate just how extreme this can be, imagine taking Earth and gradually moving it inward. First, temperatures rise, oceans begin evaporating, the atmosphere changes, eventually the surface becomes uninhabitable. Move it closer still, rock begins melting. The planet enters an entirely different category of existence. This isn't merely a hotter version of Earth, it becomes something fundamentally different, a lava world. One of the most famous examples is 55 Cancri E. This planet has fascinated astronomers for years. Located about 41 light-years away, 55 Cancri E orbits so close to its star that a year lasts less than 18 Earth hours. Think about that. By the time you finish a normal day on Earth, the planet has already completed an entire orbit. The star dominates its sky. If you stood on the surface, assuming standing was somehow possible, the star would appear enormous, far larger than our Sun appears from Earth. The resulting temperatures are staggering. Surface conditions likely exceed 2000 degrees Celsius. At such temperatures, familiar geological concepts begin behaving differently. Rock is no longer reliably solid. Entire regions may exist as vast molten oceans. Scientists have even observed variations in brightness that could indicate enormous lava flows moving across the surface. Imagine watching a weather forecast where the primary concern isn't rain or wind. It's the movement of oceans made from molten stone. The planet demonstrates that geology can become every bit as dynamic as meteorology. Another famous lava world is K2-141b. This planet may host one of the strangest environments ever proposed. Researchers believe one side permanently faces its star. The other side remains locked in darkness. This phenomenon, known as tidal locking, occurs frequently among planets orbiting close to their stars. One hemisphere experiences eternal day. The opposite hemisphere experiences eternal night. For K2-141b, the consequences are extraordinary. The day side may become hot enough to vaporize rock, not melt it, vaporize it. Minerals could enter the atmosphere as gases. Powerful winds might transport vaporized rock toward the cooler night side. There, the material could condense and fall back to the surface. In effect, the planet may experience a rock cycle resembling Earth's water cycle. Except instead of water evaporating, condensing and raining, entire minerals participate. Rock evaporates. Rock condenses. Rock rains. If someone had proposed such an environment before exoplanets were discovered, many people might have considered it unrealistic. Yet physics allows it, and nature appears happy to take advantage of that fact. A third remarkable example is Corot 7b. When Corot 7b was announced, it helped introduce the concept of lava worlds to a broader audience. The planet orbits incredibly close to its star and experiences temperatures capable of melting many rocky materials. Models suggest that enormous lava seas may cover portions of the surface. Like several other members of this category, Corot 7b likely experiences permanent day and night hemispheres. One side glows beneath intense stellar radiation, the other remains much cooler. The contrast may be among the most extreme found anywhere in planetary science. What's particularly interesting about lava planets is that they reveal what happens when ordinary rocky worlds are pushed beyond familiar limits. Take Earth. Our planet contains molten material beneath the crust. Volcanoes occasionally transport that material to the surface, yet Earth remains fundamentally solid. Lava planets reverse the relationship. Molten rock becomes dominant. Solid regions become secondary. The distinction sounds subtle. In reality, it changes everything. Mountains may form differently. Atmospheres evolve differently. Weather behaves differently. Even the appearance of the planet changes dramatically. Many lava worlds likely glow faintly from their own heat. Imagine observing a planet not because it reflects starlight, but because portions of its surface are incandescent, a dim red glow emerging from molten landscapes. The effect resembles a gigantic ember drifting through space. Researchers have detected evidence of this phenomenon on several worlds. The planets are literally hot enough to emit visible light. That's not a poetic description, it's physics. The surface becomes so hot that it begins glowing. Another fascinating aspect involves atmospheric composition. Earth's atmosphere consists primarily of nitrogen and oxygen. Lava planets often operate under entirely different rules. At sufficiently high temperatures, ordinary rock releases gases, sodium, silicon compounds, metal-bearing vapors. Atmospheres may form from ingredients rarely encountered in planetary meteorology. In some cases, the atmosphere itself may be partly composed of vaporized rock. The idea sounds bizarre because it is, yet it follows naturally from the temperatures involved. Heat changes chemistry. Extreme heat changes it dramatically. One particularly intriguing example is WASP-76b. Strictly speaking, WASP-76b is not a lava planet. It belongs to the hot Jupiter category. However, it illustrates how extreme stellar heating can become. Observations suggest temperatures high enough to vaporize metals. Studies have even proposed that iron may condense and fall elsewhere in the atmosphere. The planet demonstrates how close-in worlds often enter entirely unfamiliar physical regimes. Lava planets take similar processes and apply them to rocky surfaces. The result is a category unlike anything found in our solar system today. That last detail is worth emphasizing. The solar system currently contains no true lava planet. Mercury comes closest. It experiences intense heating. Yet even Mercury remains far cooler than worlds like 55 Cancri e or K2-141b. Our local neighbourhood simply lacks planets orbiting close enough to the Sun. This again highlights an important lesson from exoplanet science. The solar system is not a complete catalogue of planetary possibilities. Entire categories exist elsewhere that never developed here. Lava worlds are among the best examples, and yet they may not be permanent. That's one of the most interesting aspects of planetary evolution. A lava planet represents a particular state, a particular set of conditions. Change those conditions and the planet changes too. Suppose a star gradually brightens. A formerly temperate world may become increasingly hot. Eventually surface melting begins. A lava planet emerges. Alternatively, a young planet may form while still extremely hot from recent collisions. Over time it cools, its magma oceans solidify. A different planetary category appears. Planetary types are not always permanent identities. Sometimes they are stages, snapshots taken during a longer story. In fact, Earth itself may have experienced a lava world phase early in its history. Shortly after formation, our planet was dramatically hotter than it is today. Gigantic impacts occurred. Radioactive heating was intense. Large portions of the surface may have existed as magma oceans. If you could travel back more than 4 billion years, you might find a world bearing little resemblance to modern Earth. No forests, no oceans, no continents, just molten rock stretching toward the horizon. In that sense, lava planets provide windows into planetary youth. They reveal conditions that may have existed during the earliest chapters of many worlds. By studying them, scientists gain insight into how planets form and evolve. The category also raises fascinating questions about geology. What happens when entire hemispheres remain molten for millions of years? How do minerals separate? How do atmospheres interact with magma oceans? How do planetary interiors exchange heat? These questions remain active areas of research. Every new observation improves our understanding. Every newly discovered lava world adds another data point, and discoveries continue arriving. The galaxy appears surprisingly willing to produce these infernal environments. Close-in rocky planets are common, many orbit stars smaller than the Sun, others circle stars larger and hotter. Different stellar systems create different versions of the same basic theme: too much heat, too much radiation, too much energy concentrated onto a rocky surface. The result is a world where geology behaves like weather, where stone flows, where mountains melt, where landscapes glow, where rock becomes liquid. Most planets fall into categories that sound reasonably familiar. Rocky planets, ocean planets, gas giants, ice giants, even lava worlds, extreme as they are, can still be understood using concepts we recognize. Heat rock enough and it melts. Add enough gas and a giant planet forms. Remove water and a desert appears. The basic ingredients remain recognizable. Then astronomy occasionally encounters a world that seems determined to ask a different question. What happens if the recipe itself changes? What happens if a planet forms in an environment with unusual chemistry? What happens if carbon becomes one of the dominant building materials? What happens if conditions become so extreme that entire worlds may contain vast quantities of diamond? This is where planetary science begins to feel less like geography and more like a cosmic laboratory. Among the thousands of planets discovered so far, a handful stand out because they hint at possibilities that sound almost fictional. Not because anyone invented them, because nature appears willing to experiment, and sometimes those experiments produce worlds unlike anything in our own solar system. Carbon worlds belong to this category. So do the famous diamond planet candidates. They remain among the most exotic planetary types ever proposed, and while many details remain uncertain, the science behind them is fascinating. To understand why, it helps to think about Earth's composition. Our planet formed primarily from oxygen-rich and silicon-rich materials. Silicate rocks dominate much of the crust. Oxygen is abundant. Iron is abundant. Various minerals combine to create the landscapes we know. Mountains, valleys, volcanoes, continents. Earth's geology reflects the ingredients available during formation. Change those ingredients and entirely different worlds may emerge. Imagine a planetary system forming within a region where carbon is unusually abundant relative to oxygen. The chemistry changes. Instead of producing primarily silicate-rich worlds, the environment may favour carbon-rich materials. Theoretical models suggest such planets could develop very different interiors, very different crusts, very different geological histories. Scientists call these hypothetical objects carbon planets. Unlike Earth, where carbon represents only a relatively small fraction of the planet's mass, carbon worlds could contain enormous quantities of carbon-bearing minerals, graphite, carbides, possibly diamonds. The result would not merely be a different version of Earth, it would be a fundamentally different kind of planet. The landscapes might look unfamiliar. The geology might behave differently. Even the atmosphere could evolve along unusual pathways. At present, astronomers have not definitively confirmed a pure carbon world. But several fascinating candidates exist. One of the most famous is 55 Cancri E. We've already encountered 55 Cancri E in our discussion of lava planets. This remarkable world continues appearing in planetary science because it may belong to multiple interesting categories at once. The planet orbits astonishingly close to its star. Temperatures are extreme. A year lasts less than 18 hours, and early studies suggested something particularly intriguing. The host star appeared relatively rich in carbon. That raised a possibility. Perhaps the planet itself formed in a carbon-rich environment. If so, enormous quantities of carbon-bearing materials could exist within its interior. Some researchers even propose that substantial portions of the planet might consist of diamond. Newer observations have complicated that picture. The evidence is less certain than initially believed, yet 55 Cancri E remains one of the most famous examples of how unusual planetary chemistry might become. Even if the planet turns out not to be a giant diamond, it still demonstrates that planetary formation can produce worlds very different from Earth, and that realization alone is important. Then there is one of the strangest objects ever discovered, PSRJ 1719-1438b. If planetary science awarded prizes for unusual life stories, this world would be a serious contender. First, consider its star, or rather, what remains of its star. PSRJ 1719-1438b orbits a pulsar. A pulsar is the incredibly dense remnant left behind after a massive star explodes as a supernova. Imagine compressing a star into an object only a few kilometers across, while retaining much of its mass. The result is a neutron star. Some neutron stars rotate rapidly and emit beams of radiation. These become pulsars. Already we're dealing with one of the most extreme environments in the universe. Then astronomers discovered a companion object. At first glance it appeared planetary, yet its density seemed extraordinary. Researchers proposed a remarkable possibility. The object might actually represent the stripped core of a former star. Over immense spans of time, the pulsar's gravity may have removed the outer layers of a companion star, leaving behind a dense carbon-rich remnant. Under such conditions, much of the remaining carbon could exist in crystalline form. In popular media, PSRJ 1719-1438b quickly became known as the Diamond Planet. Technically, reality is somewhat more complicated. The object is not literally a giant jewelry store floating through space, yet the underlying idea remains astonishing. an entire planetary mass object potentially composed largely of crystalline carbon. The universe has a way of making even the most extravagant concepts sound plausible. Another fascinating candidate is WASP-12b. Unlike 55 Cancri E or PSR-J 1719-1438b, WASP-12b is not a rocky world. It belongs to the hot Jupiter category. Nevertheless, it became famous because atmospheric observations suggested unusually carbon-rich chemistry. The planet orbits incredibly close to its star, so close in fact that stellar gravity is actively stretching it. Material from the atmosphere is gradually escaping. The world is essentially being pulled apart. Despite belonging to a different planetary category, WASP-12b helped strengthen scientific interest in carbon-rich planetary systems. If stars and planets form from carbon-rich environments, then unusual chemistry may emerge throughout entire planetary families, not just on one world, potentially on several. And that possibility significantly expands the range of planets nature can create. What's particularly fascinating about carbon planets is how different their geology might become. Earth's geology relies heavily on silicates. Volcanic processes involve familiar minerals. Mountain building follows patterns shaped by oxygen-rich chemistry. A carbon-rich world could behave differently. Researchers have proposed crusts dominated by graphite, layers rich in carbides, different mantle structures, different volcanic products. Even the appearance of the landscape could change. Imagine standing on a world where the dominant rocks differ fundamentally from those found on Earth. The mountains might reflect light differently. The surface colour could vary dramatically. Weathering processes might produce unfamiliar terrain. It's difficult to predict exactly because we lack direct examples, and that uncertainty is part of what makes the category so intriguing. Then there is the question everyone inevitably asks. If a planet contains diamonds, how much would those diamonds be worth? The answer is amusing. Probably much less than people imagine. Value depends heavily on rarity. Diamonds remain valuable partly because they are relatively uncommon on Earth. If entire planets contain vast quantities of diamond, the concept of scarcity begins breaking down rather dramatically. More importantly, nobody is transporting planetary masses of diamond across interstellar distances anytime soon. The practical challenges are substantial, to put it mildly. Still, the idea captures public imagination because it combines two things humans find fascinating: precious materials and distant worlds. The result is irresistible. Yet the true scientific importance lies elsewhere. Carbon planets remind us that planetary formation depends on chemistry. Different ingredients produce different outcomes. The solar system represents one example, not the example, one recipe among countless possibilities. Some stars contain different elemental ratios. Some planetary disks evolve differently. Some worlds inherit unusual compositions. The diversity that emerges can be extraordinary. Another interesting aspect involves atmospheric evolution. Atmospheres form through interactions between planetary interiors, stellar radiation, and chemical processes. Change the underlying composition and atmospheric chemistry changes too. Carbon-rich planets might develop atmospheric environments unlike anything found in our solar system. Theoretical models predict a wide variety of possibilities. Methane-rich atmospheres, carbon monoxide-rich atmospheres, complex hydrocarbon chemistry, different cloud systems, different climate dynamics. Again, direct observations remain limited. Future telescopes will provide much better data. For now, researchers rely on models and indirect measurements. One thing becoming increasingly clear is that planetary diversity extends far beyond size and temperature. For a long time, astronomers focused primarily on mass, radius, orbital distance. Those measurements remain important, but chemistry matters too. A rocky planet is not simply a rocky planet. Its internal composition matters, its elemental abundance matters, its formation history matters. Two worlds with identical sizes may possess dramatically different interiors. Carbon planets illustrate that principle beautifully. Perhaps the most remarkable thing about these exotic worlds is that they demonstrate how creative nature can be. When humanity first began studying planets, the solar system seemed sufficient. 8 major planets, a few dwarf planets, various moons and asteroids, interesting certainly, but manageable. Then exoplanets arrived. Suddenly entirely new categories appeared. Hot Jupiters, super-Earths, mini-Neptunes, lava worlds, potential carbon planets, potential diamond planets. The universe kept revealing additional possibilities. Every discovery expanded the menu, and there is little reason to believe the process has ended. Future surveys will almost certainly uncover even stranger examples. Worlds with unexpected chemistry, unexpected structures, unexpected histories. That's one of the great lessons of planetary science. Nature is rarely limited by human imagination. More often, human imagination struggles to keep up with nature. Not every planet remains loyal to its star. For most of the worlds we've visited so far, a star has always been part of the story. Mercury races around the Sun, Earth circles the Sun, Jupiter and Saturn orbit the Sun. Even the distant exoplanets discovered around other stars remain gravitationally attached to their stellar parents. A star provides warmth, light, energy, a centre to orbit, a fixed point around which an entire planetary system organises itself. It feels natural, almost inevitable. After all, that is how planets are supposed to behave, or so we once thought. Then astronomers began uncovering evidence for something far stranger. Planets with no star. Worlds that travel through the darkness alone. No sunrise, no sunset. No parent star dominating the sky. No year, no familiar seasons. Only an endless journey through interstellar space. These are rogue planets, and among all the planetary types we've discussed, they may be the most isolated objects in the galaxy. In a sense, rogue planets are cosmic runaways, worlds that somehow lost their place in a planetary family and were cast into the darkness between stars. The idea sounds dramatic, almost tragic, yet the physics behind it is surprisingly straightforward. Planetary systems are not always peaceful places. During the early stages of formation, gravity creates chaos. Multiple worlds compete for stable orbits. Giant planets migrate, objects collide, orbital paths shift constantly. Imagine a crowded dance floor where everyone is moving unpredictably. Occasional collisions become unavoidable. Planetary systems can behave similarly. In many young systems, gravitational interactions become violent enough to completely eject a planet. One close encounter with a giant world may be all it takes. The unfortunate planet receives a gravitational shove. Its orbit stretches. The shove grows stronger. Eventually escape velocity is reached. The world breaks free forever. The star's grip weakens, then disappears. The planet becomes a wanderer. For a long time, astronomers suspected this process should occur. Computer simulations repeatedly produced rogue planets, yet suspicion and evidence are different things. The question remained, do these worlds actually exist? The answer appears to be yes, and perhaps in enormous numbers. One of the most famous examples is CFB DSIR 2149-0403. Discovered drifting through space without an obvious stellar companion, this object became one of the strongest rogue planet candidates known. Its exact nature remains under investigation. Researchers continue refining measurements. Nevertheless, it helped demonstrate that planetary mass objects can exist independently of stars. Another important example is PSOJ 318.5-22. This remarkable world possesses characteristics similar to giant exoplanets. Yet no parent star accompanies it. The object drifts alone through space. Observations suggest an atmosphere rich in clouds and weather systems. Imagine that for a moment. A planet-sized object experiencing weather despite having no nearby sun. The universe remains determined to challenge expectations. Then there is WISEAJ 1147 24.10-2 0402.1.3. The name is admittedly less memorable than Jupiter or Saturn. Astronomers occasionally favour precision over marketing, yet this object represents another important piece of evidence supporting the existence of planetary mass wanderers. Together, discoveries like these transformed rogue planets from theoretical curiosities into legitimate members of the planetary family. And the numbers may be astonishing. Some studies suggest rogue planets could rival stars in abundance. Think about that carefully. The Milky Way contains hundreds of billions of stars. If rogue planets are similarly common, then countless dark worlds may drift through interstellar space unseen, not orbiting stars, not belonging to planetary systems, simply travelling, alone. The scale of that population is difficult to comprehend. For every familiar planetary system illuminating the darkness, there may be wandering worlds moving silently between them. The next question naturally follows. What would it actually be like on a rogue planet? The answer depends heavily on the planet itself. A recently ejected gas giant would differ dramatically from a small rocky world. A young rogue planet would differ from an ancient one. Yet certain themes appear repeatedly. The most obvious is darkness. Without a nearby star, illumination becomes scarce, extremely scarce. Imagine standing outside on a clear night. The moon is absent. City lights are absent. Only starlight remains. Now remove the stars as well. Or reduce them to tiny distant points. That's closer to what a rogue planet experiences. Its sky would not resemble Earth's. No bright sun dominates the heavens. Instead, distant stars provide faint illumination. Perhaps a bright neighbouring galaxy appears overhead. Maybe a few nearby stars shine more strongly than others. But daytime never arrives. The planet exists in permanent night. At first glance, such a world sounds completely frozen. And many rogue planets probably are. Temperatures would inevitably decline after losing stellar heating. Surface water would freeze. Atmospheric gases might condense. The landscape could become locked beneath layers of ice. Yet surprisingly, complete freezing is not always guaranteed. Planets possess another source of energy, their interiors. Earth itself continuously generates heat. Radioactive elements decay within the mantle. Residual heat from formation remains trapped below the surface. Volcanic activity releases some of that energy. Even today, geothermal heat contributes to Earth's overall energy budget. On a rogue planet, internal heat may become critically important. Imagine an Earth-sized world wrapped beneath a thick insulating atmosphere. Even without sunlight, geothermal energy could maintain surprisingly warm conditions in some regions. The surface might remain frozen. Deep beneath, liquid water could persist. Researchers have explored this possibility for years. Under the right circumstances, a rogue planet might support subsurface oceans despite drifting through interstellar space. The idea sounds extraordinary. A dark world between the stars containing hidden oceans beneath ice. Yet the underlying physics appears plausible. In some scenarios, thick hydrogen atmospheres could provide additional insulation. Hydrogen is often associated with giant planets, but certain rogue worlds may retain substantial amounts. That atmosphere acts like a blanket. Heat escapes more slowly. Temperatures remain higher than expected. Again, we encounter a recurring lesson. Planetary environments are rarely as simple as they first appear. Darkness does not automatically mean inactivity. Cold does not automatically mean geological death. The universe repeatedly demonstrates surprising resilience. One particularly fascinating possibility involves life. Not because scientists believe rogue planets are likely homes for advanced civilizations. There is currently no evidence for that. Rather because some conditions may permit microbial ecosystems. If liquid water exists beneath the surface and energy sources remain available, life becomes conceivable. Earth offers an interesting comparison. Deep beneath our oceans, hydrothermal vents support entire ecosystems independent of sunlight. These communities rely on chemistry rather than photosynthesis. The sun plays little direct role. If such systems can exist here, perhaps analogous environments could exist elsewhere. Even on worlds that never experience daylight, at present this remains speculative, but it is scientifically reasonable speculation, and it highlights how discoveries often expand our definition of habitability. A few decades ago, many researchers focused almost exclusively on Earth-like environments. Today the conversation includes ocean worlds, subsurface oceans, ice-covered moons, and even rogue planets. The more we learn, the broader the possibilities become. Another intriguing aspect of rogue planets involves their origins. Not every free-floating planetary mass object necessarily began as a conventional planet. Some may have formed directly from collapsing clouds of gas, similar to stars. If so, the distinction between planets and very small brown dwarfs becomes complicated. Again, nature resists simple categories. Astronomers continue debating exactly where the boundaries should be drawn, and that's perfectly normal. The universe rarely organises itself according to human filing systems. Sometimes categories overlap, sometimes they blur, sometimes entirely new categories emerge. Rogue planets occupy one of those blurry regions. Their existence forces scientists to reconsider traditional definitions. What truly makes a planet a planet? Is it composition, mass, formation history, orbital behaviour? The answer becomes less obvious once worlds start wandering independently. Detection presents another challenge. Finding ordinary exoplanets is already difficult. Finding rogue planets is much harder. A planet orbiting a star periodically blocks starlight. Astronomers can detect that. A rogue planet provides no such convenient signal. Instead, researchers often rely on a phenomenon called gravitational microlensing. According to Einstein's theory of gravity, massive objects bend space. When a rogue planet passes in front of a distant star, its gravity briefly magnifies the star's light. The effect is subtle, temporary, easy to miss, yet it provides a powerful detection method. Several rogue planet candidates have emerged through exactly this technique. One famous example involves observations by collaborations such as OGLE and MEOA, which have helped identify potential populations of free-floating planets. The results remain an active area of research. Some studies suggest vast numbers, others suggest somewhat smaller populations. Either way, rogue planets appear real, and they appear important. Perhaps the most remarkable thing about rogue planets is how completely they alter our intuition. For centuries, planets and stars seemed inseparable. Planets orbited stars. That was simply what planets did. Now we know otherwise. A planet can lose its star. It can survive the ejection. It can continue existing for billions of years. It can travel through the galaxy alone. The universe allows that possibility. And once you accept it, the Milky Way becomes an even stranger place. Between the bright stellar systems we normally imagine may lie countless unseen worlds, frozen worlds, dark worlds, possibly ocean-bearing worlds, worlds that once belonged somewhere else, worlds that have spent hundreds of millions or even billions of years crossing the enormous distances between stars, silent travellers moving through an ocean of darkness. For most of human history, the sky seemed wonderfully predictable. The sun rose in the east, it crossed the sky, it set in the west. The moon followed its familiar cycle, the planets wandered slowly against the background stars. Everything appeared orderly. If someone had suggested that entire worlds might experience two suns rising at once, many people would probably have placed the idea firmly in the realm of mythology. It sounds like something from a fantasy story, or perhaps a science fiction film, a distant desert beneath twin sunsets. Two shadows stretching across the ground, a sky illuminated by multiple stars. For a long time, such images belonged almost entirely to imagination. Then astronomers started discovering exoplanets, and once again, reality proved perfectly capable of competing with fiction. Today we know that planets orbiting two stars are real, not theoretical, not speculative, real worlds moving through real planetary systems. And once scientists found those planets, they discovered something even more interesting. The universe is remarkably creative when it comes to orbital design. Not every planet follows a simple circular path around a single star. Some orbit two stars, some follow highly elongated trajectories, some move through complex resonant patterns alongside neighbouring worlds, some experience seasons unlike anything found in the solar system. Some may even orbit stars, moving around each other in elaborate gravitational dances. If planetary types describe what planets are made of, orbital architecture describes how they live, and some of those orbital lives are extraordinarily strange. The most famous category is the circumbinary planet. The name sounds technical, but the idea is straightforward. A circumbinary planet orbits two stars instead of one. Imagine two stars gravitationally bound together. They circle a common centre of mass. Meanwhile, farther out, a planet orbits both stars as though they were a single object. The result resembles a cosmic dance involving three participants. For decades, scientists suspected such arrangements should be possible. Physics certainly allowed them. The challenge was determining whether nature actually built them. The answer arrived in spectacular fashion. One of the most famous examples is Kepler-16b. Discovered in 2011, Kepler-16b immediately attracted worldwide attention. The reason was simple. This was essentially a real version of the famous twin-sun planet from science fiction. The planet orbits two stars. A resident standing on such a world, assuming the planet possessed a suitable surface, might occasionally witness two suns in the sky, sometimes close together, sometimes farther apart, sometimes one brighter than the other. The exact appearance would depend on the orbital positions involved. Yet the basic idea remains extraordinary: a double sunset, a double sunrise, not imagination, astronomy. Kepler-16b itself is a gas giant, so nobody is standing on its surface. Still, the discovery proved that circumbinary worlds exist, and once astronomers found one, additional examples quickly followed. As often happens in science, the first discovery opened a door. Suddenly researchers knew what to look for. Soon the list began growing. Another fascinating example is Kepler-47c. The Kepler-47 system attracted attention because it contains multiple planets orbiting a pair of stars. This was particularly important. A single circumbinary planet might be unusual. An entire planetary system suggested something deeper. Nature wasn't merely allowing these arrangements, it was producing them repeatedly. The implications were profound. Planet formation appeared more flexible than many researchers had assumed. For a long time, binary star systems were considered challenging environments for planet formation. The gravitational influence of two stars seemed potentially disruptive. Yet planets formed anyway. Nature found a way, as it often does. Then there is Kepler-453b. This world helped demonstrate how complex orbital mechanics can become. The planet's transits don't occur with perfect regularity because the stars themselves are moving. From Earth's perspective, the timing changes. Detecting and analysing such systems requires extraordinary precision. Astronomers must account for multiple moving bodies simultaneously. It's a bit like trying to predict the motions of dancers on a stage while viewing the performance from hundreds of kilometres away. The mathematics becomes intricate. The rewards are worth it. What's especially interesting about circumbinary planets is that their climates may differ dramatically from those of ordinary worlds. On Earth, the Sun provides a relatively stable source of illumination. Circumbinary worlds may experience more complicated patterns. The brightness of the sky changes depending on the positions of both stars. Seasons could become more complex. Daylight conditions could vary in unfamiliar ways. Even shadows might behave differently. Imagine walking across a landscape while two separate stars illuminate the terrain. Multiple shadows might appear. The sky itself could look entirely different from anything humans have experienced. And yet circumbinary planets are only the beginning. The universe has many other orbital surprises to offer. One particularly important concept involves orbital eccentricity. Most diagrams show planets moving in nearly circular paths. Earth does this, Venus does this, Neptune does this. However, not every planet enjoys such stable geometry. Some follow highly elongated orbits. At one point in the orbit, the planet approaches relatively close to its star. Later, it travels much farther away. The resulting changes in temperature can be dramatic. A famous example is HD 80606b. This remarkable world follows one of the most elongated planetary orbits ever observed. At its closest approach, temperatures rise rapidly. The atmosphere responds violently. The planet experiences dramatic heating events unlike anything seen in the solar system. Imagine a year where the climate changes not gradually but abruptly. A world moving between vastly different environments during a single orbit. Nature permits that too. Another fascinating phenomenon involves orbital resonance. This occurs when planets influence one another through regular gravitational relationships. The solar system contains several examples. Jupiter's moons provide particularly beautiful demonstrations. Beyond our solar system, resonant systems appear frequently. One of the most famous examples is the TRAPPIST-1 system. We've briefly encountered TRAPPIST-1 before. The system contains 7 known rocky planets. What's especially remarkable is that their orbital periods form a resonant chain. Each planet influences its neighbours in a predictable way. The arrangement resembles an intricate piece of celestial clockwork. Nothing is random. Every orbit contributes to the larger pattern. Watching such a system evolve over time would be like observing a gravitational symphony. Each planet plays its part. The entire system moves together. These resonances also provide clues about planetary history. They often indicate that planets migrated after formation. Worlds formed in one location, then moved. Interactions gradually guided them into stable relationships. By studying orbital patterns, astronomers can reconstruct events that happened billions of years ago. The planets preserve their own history in their motions. Some exotic systems become stranger still. Consider planets orbiting pulsars. We've already encountered one example when discussing potential diamond worlds. A pulsar is the remnant of a massive star that exploded. Logic might suggest that planets should not survive such violence, and many do not, yet some apparently do. One famous example is PSRB 1257+12 system. Remarkably, the first confirmed exoplanets ever discovered orbited a pulsar. The discovery shocked astronomers. At the time, many researchers expected the first exoplanets to be found around ordinary stars. Instead, the honour went to a system orbiting a stellar corpse. The universe once again demonstrated its talent for surprising people. Imagine standing on a planet illuminated not by sunlight but by a neutron star. The environment would be profoundly alien, yet the planets exist. Reality is under no obligation to prioritise familiarity. Then there are planets in multiple star systems more complicated than simple binaries. Some stars belong to groups of 3 or more. Planets can occupy stable orbits within these environments as well. The resulting gravitational interactions become increasingly complex. Computer simulations help researchers identify which configurations remain stable over long periods. Some arrangements survive for billions of years. Others collapse quickly. Planetary systems must balance on a delicate gravitational framework. One particularly interesting consequence of exotic orbits involves habitability. A planet's climate depends heavily on the energy it receives from its star. Change the orbit and the climate changes too. A highly eccentric orbit may create extreme seasonal variations. A circumbinary orbit introduces multiple sources of illumination. Resonant interactions can affect rotation rates and tidal heating. The orbital architecture becomes part of the environmental story. Habitability is not merely about distance from a star. It is about motion, rhythm, long-term stability. The entire gravitational context matters. Perhaps the most important lesson from these discoveries is that planetary systems are not standardized products. There is no universal blueprint, no mandatory arrangement. The solar system represents one solution. Kepler-16 offers another. TRAPPIST-1 offers another. Thousands more continue emerging from the data. Each system tells a different story. Each demonstrates a different way of organizing worlds around stars. Millions of years from now, long after today's telescopes have been retired, long after current observatories have become museum pieces, future astronomers may look back at our era and smile, not because we were wrong, not because our discoveries lacked value, but because we were only beginning. In many ways, humanity currently occupies a fascinating moment in the history of planetary exploration. We've learned enough to realize how little we know. We've discovered enough planets to understand that the universe is astonishingly diverse. Yet we've only examined a tiny fraction of what is actually out there. A very tiny fraction. Imagine standing on a beach and collecting a single handful of sand. Now imagine trying to understand every beach on Earth using only those grains. That comparison may actually underestimate the challenge. The Milky Way alone contains hundreds of billions of stars. Many of those stars host planets. Some host multiple planets. Some may host entire planetary families more complex than our own solar system. And beyond the Milky Way lie hundreds of billions of additional galaxies. The numbers become so large that the mind naturally begins resisting them. Not because the numbers are incorrect, because human brains were never designed to think comfortably in terms of trillions upon trillions of worlds, and yet those worlds exist. Somewhere. Right now. As we've travelled through the planetary zoo together, a remarkable pattern has emerged. Nature does not seem interested in repeating itself. Again and again, we encountered planets that challenged expectations, rocky worlds larger than Earth, mini-Neptunes absent from our solar system, ocean planets potentially covered by global seas, desert planets that lost their water, ice giants wrapped in blue atmospheres, lava worlds where rock behaves like liquid, carbon-rich planets, potential diamond planets, rogue planets wandering between the stars, planets orbiting two suns. Each category expanded our understanding of what a planet can be. Yet perhaps the most important lesson is that every category began with a discovery. At some point, nobody knew lava planets existed. At some point, nobody knew mini-Neptunes existed. At some point, nobody knew rogue planets existed. The categories were absent because the observations were absent. Then new instruments arrived. New data appeared. The universe revealed another surprise, and another, and another. There is every reason to believe the process will continue. Future astronomers may eventually discover entire planetary categories that we have not yet imagined. Not because today's scientists lack creativity, because nature is extraordinarily inventive. History consistently demonstrates that the universe contains possibilities beyond our expectations. Consider how much has changed in only a few decades. Before the 1990s, humanity knew of exactly one planetary system. One. The solar system. Today, astronomers have confirmed thousands of exoplanets. Entire scientific fields now exist that would have sounded speculative only a generation ago. Researchers study atmospheric chemistry on distant worlds. measure temperatures on planets hundreds of light years away, analyze cloud structures in alien skies, search for biosignatures, model climates unlike anything found on Earth. The progress has been remarkable, and yet we remain at the beginning. Many of the most powerful telescopes ever constructed are only now beginning their work. The James Webb Space Telescope is already transforming planetary science. Future observatories will push even further: larger mirrors, more sensitive instruments, better atmospheric measurements, sharper observations. Some upcoming projects aim to study Earth-sized planets directly, not merely detect them, study them, characterize them, examine their atmospheres, search for chemical signatures. The dream that motivated generations of astronomers is gradually becoming reality. For the first time in history, humanity is approaching the ability to investigate distant worlds in meaningful detail, and when that happens, surprises are inevitable. Perhaps we'll discover true ocean planets with atmospheres rich in water vapour. Perhaps we'll find carbon worlds more exotic than current models predict. Perhaps we'll identify entirely new planetary structures. Hycean worlds have already entered scientific discussion. These hypothetical planets combine deep oceans with hydrogen-rich atmospheres. A few decades ago, nobody would have included such worlds in a planetary classification scheme. Now researchers actively investigate them. What comes next? Nobody knows. And that's precisely what makes the future exciting. There may be worlds composed primarily of materials rarely encountered in our solar system. Worlds shaped by unusual stellar environments. Worlds orbiting stars unlike any we've studied closely. Worlds that challenge existing theories. Planetary science thrives on such discoveries. Each unexpected world forces researchers to reconsider assumptions. The map expands, the definitions evolve, understanding deepens. Another fascinating possibility involves planets around entirely different kinds of stars. Red dwarfs already appear capable of hosting enormous planetary populations, but what about stars substantially smaller than the Sun? What about stars much larger? What about unusual stellar remnants? The universe contains extraordinary variety among stars. That variety inevitably influences planetary formation. Every new environment creates opportunities for new outcomes. The diversity we've already observed may represent only a small sample of what is possible. Some researchers have even suggested that there may be planetary categories we currently cannot detect effectively. Detection methods influence discovery. Astronomers find certain planets more easily than others. Large planets are often easier to detect. Close-in planets produce stronger signals. Certain orbital arrangements reveal themselves more readily. As technology improves, previously hidden populations may emerge. It's possible that some of the galaxy's most common planetary types remain largely undiscovered simply because our instruments have not yet reached the necessary sensitivity. History suggests caution when assuming we've seen everything. We almost certainly have not. But beyond all the scientific details lies a deeper question. What does planetary diversity actually tell us? What does it mean? After all, discovering thousands of worlds is impressive. Understanding their significance is something else entirely. One lesson stands out above all others. Earth is neither the centre of planetary possibility nor the endpoint of planetary evolution. For much of history, humanity naturally viewed Earth as the standard, the reference point, the normal world, the place against which everything else would be compared. Exoplanet discoveries change that perspective. Earth remains special to us. It is our home, the only known world that hosts life. The only place where oceans, forests, mountains, cities and people coexist. Nothing can replace that significance, yet Earth is also one example among countless planetary outcomes. One successful solution to the challenge of building a world. Not the only solution. Not necessarily the most common solution. Simply one solution. That realization can feel humbling, and it should. The universe is larger and more varied than previous generations imagined. The diversity of planets demonstrates this beautifully. Nature does not repeatedly produce copies of Earth. It experiments, again and again. Different ingredients, different temperatures, different atmospheres, different histories, different outcomes. Every world becomes a unique story. And yet Earth's uniqueness remains undiminished. In fact, planetary diversity may enhance our appreciation for it. Consider everything required for modern Earth to exist. A stable star, long-term climate stability, persistent liquid water, active geology, a magnetic field, the right chemical ingredients, billions of years of uninterrupted evolution. The more planets we discover, the more remarkable that combination appears. Not because Earth is the only habitable world. We do not know whether it is, but because planetary science reveals how many ways a planet can become something else. A desert, a lava world, a gas giant, a frozen wasteland, a rogue wanderer. Earth followed a particular path through a vast landscape of possibilities, and here we are, tiny creatures on the surface of a rocky planet orbiting an ordinary star, studying worlds we may never visit, measuring atmospheres across unimaginable distances, trying to understand our place within a galaxy crowded with planets. There is something wonderfully human about that effort. For thousands of years our ancestors looked upward and wondered, what are the wandering lights? How many worlds exist? Are we alone? What else is out there? Today we possess better answers than any generation before us. Not complete answers, better ones. And every year those answers improve. Every telescope adds another piece. Every discovery extends the story. Every new world expands the map. Perhaps one day humanity will visit another planetary system. Perhaps robotic explorers will land on distant worlds. Perhaps future civilizations will look back on these early discoveries the way we look back on the first maps of unknown continents. The beginning of a much larger journey. For now, though, there is something comforting about simply appreciating the scale of what we've learned. The universe contains rocky worlds and ocean worlds, desert worlds and frozen worlds, gas giants and ice giants, lava planets and wandering rogues, planets orbiting one sun, planets orbiting two, planets that challenge imagination itself, and somewhere among them are almost certainly worlds we have not yet discovered, worlds waiting quietly in the darkness. Worlds that will someday receive names, worlds that will someday force scientists to invent entirely new categories, worlds that will remind future generations of the same lesson the universe has been teaching all along. Reality is larger than expectation. The planetary zoo is far bigger than we once believed, and despite everything we've learned, countless exhibits remain unexplored. As you settle a little deeper into your pillow and let the vast collection of worlds drift gently through your thoughts, it's worth remembering that every planet we've discussed tonight, from the familiar rocky worlds to the lonely wanderers between the stars, shares one simple connection. They all exist within the same universe that produced Earth, the same universe that produced us. And somewhere beyond the reach of today's telescopes, beyond the limits of current maps, beyond the edge of what we presently know, the next planetary surprise is already waiting.